Deep in the Amazon rainforest, where sunlight barely penetrates the triple canopy jungle, explorers made a discovery that shouldn't exist. Using cutting-edge LiDAR technology that strips away vegetation to reveal what lies beneath, archaeologists identified geometric patterns stretching across hundreds of square kilometers. Earthworks, roadways, the unmistakable signatures of urban planning. But these weren't the ruins of some forgotten village. What emerged from the data suggested cities vast, sophisticated, and utterly unknown to history. Tonight, we're descending into 3 hours of Amazon expeditions that rewrote everything we thought we knew about pre-Columbian civilization. From lost cities buried under centuries of vegetation to artifacts that challenge our timeline of human achievement, these are the discoveries that left explorers speechless. Let's begin in the Bolivian Amazon, where the jungle was hiding something extraordinary. The drought theory. Paleoclimate research using lake sediment cores and speleothem records from Amazonian caves has reconstructed rainfall patterns stretching back thousands of years. This data reveals that the period between 900 and 1250 AD, when Kasarabe civilization was at its peak, experienced several severe drought episodes. Some of these droughts, identified through oxygen isotope analysis, reduced rainfall by up to 40% for periods lasting decades. Initially, researchers assumed these droughts would have stressed Kasarabe society, but a closer examination of the archaeological record revealed something unexpected. The largest construction projects and the most elaborate artifacts dated precisely to these drought periods. This suggests that rather than causing collapse, the droughts may have driven social innovation, forcing the development of the sophisticated water management systems that characterized Kasarabe engineering. The civilization's eventual collapse around 1400 AD came after these drought cycles had ended, suggesting the relationship between climate and social stability was more complex than simple environmental determinism. The paleoclimate reconstruction relied primarily on 3 types of evidence. Lake sediment cores extracted from several lakes in the Llanos de Moxos provided continuous records spanning 3,000 years. Each annual layer of sediment preserved chemical signatures that reflected rainfall amounts. Oxygen isotope ratios in carbonate minerals showed particularly clear patterns. Higher ratios indicated drier conditions with more evaporation. Lower ratios indicated wetter periods. Speleothems, mineral deposits that form in caves, including stalagmites and stalactites, provided a second line of evidence. These formations grow gradually as water drips through caves, depositing thin layers of calcium carbonate. Each layer records the isotopic composition of rainwater at the time of deposition. By analyzing growth bands similar to tree rings, researchers reconstructed rainfall variations with annual or even seasonal resolution. The third evidence source came from tree ring analysis of subfossil wood preserved in wetland environments. Though tropical trees don't typically produce clear annual rings, some species show growth variations related to seasonal flooding cycles. Cores from these trees provided year-by-year records of environmental conditions. When combined, these 3 data sources revealed a consistent pattern. The period from 900 to 1250 AD experienced higher baseline aridity than preceding or following centuries, punctuated by several severe drought episodes. The most intense droughts occurred around 920 to 940 AD, 1020 to 1050 AD, and 1140 to 1170 AD. Each drought lasted 20 to 30 years and reduced rainfall by 30 to 40% compared to long-term averages. The archaeological correlation emerged when researchers compared radiocarbon dates from major construction projects against the climate chronology. The largest platform mounds at Kotoka showed construction phases dating to 930 to 950 AD and 1150 to 1180 AD, precisely during or immediately after the major drought episodes. Similarly, the most sophisticated water management features, including the underground canal systems, dated to the drought periods. This pattern suggested a counterintuitive relationship between environmental stress and social investment. Rather than droughts causing societal breakdown, they appeared to stimulate innovation and collective action. Communities facing water scarcity may have mobilized around large-scale infrastructure projects, building reservoirs and distribution systems that not only addressed immediate needs, but also demonstrated and reinforced social cohesion during challenging times. The collapse after 1400 AD occurred during a period of relatively normal rainfall, adding complexity to the environmental explanation. If drought stimulated innovation and construction, why did the civilization collapse during better conditions? Some researchers proposed that the water management systems, optimized for drought conditions, may have actually failed during periods of excessive flooding. The channels and reservoirs designed to capture and store scarce water might have been overwhelmed when rainfall returned to normal levels, causing flooding and agricultural disruption. The satellite cities, while the largest Kasarabe sites like Kotoka and Landivar garnered the most attention, systematic LiDAR surveys revealed a hierarchy of settlements spreading across the landscape. Surrounding the two major urban centers were dozens of smaller sites, ranging from 20 to 50 hectares in size, each featuring their own platform mounds and earthworks, though on a smaller scale. These sites were connected to the major centers by causeways and were positioned at regular intervals roughly 20 kilometers apart, suggesting deliberate planning of settlement distribution across the region. Excavations at several of these secondary sites revealed that they specialized in different activities. One site showed evidence of extensive ceramic production, with pottery kilns and clay processing facilities. Another appeared to focus on fish processing, with thousands of fish bones and evidence of smoking and drying facilities. This economic specialization suggested these weren't independent settlements, but rather integrated components of a larger urban system centered on the major cities. The settlement hierarchy became apparent when LiDAR data was analyzed using spatial statistics. Researchers mapped all identified sites and calculated their spacing, size distributions, and connectivity through causeways. The analysis revealed a clear three-tiered system. At the top were the two major urban centers, Kotoka and Landivar, each exceeding 100 hectares with platform mounds over 20 meters high. The middle tier consisted of approximately 24 sites ranging from 20 to 50 hectares, with platform mounds of 8 to 15 meters height. The bottom tier included over 60 small sites of less than 10 hectares, featuring modest earthworks but few substantial structures. The spatial distribution showed non-random patterning. The middle tier sites formed a roughly circular arrangement around each major center, with spacing between sites averaging 18 to 22 kilometers, a distance that represented approximately one day's travel on foot. This suggested the regional landscape was organized into territories, with each secondary site serving as a local center for its surrounding area, while remaining connected to the primary urban centers. Excavation at a site designated SM14, located 19 kilometers northeast of Kotoka, revealed its specialized function. The site covered 32 hectares and featured a central platform mound 11 meters high. Surrounding this central feature were numerous low mounds and depressions that initial surveys hadn't recognized as artificial features. Systematic excavation revealed these were the remains of pottery production facilities. The pottery kilns were distinctive structures. Each consisted of a clay-lined pit, approximately 2 meters in diameter and 1.5 meters deep, with a channel leading to a smaller fire pit. The configuration allowed hot gases from the fire to circulate through the main chamber, where pottery was stacked for firing. At least 15 such kilns were identified across the site, suggesting large-scale production far exceeding local needs. The clay processing areas showed equal specialization. Large, shallow basins lined with fired clay served as levitation facilities, where clay was mixed with water, allowing impurities to settle out while fine clay particles remained suspended. This purified clay produced higher quality pottery. Chemical analysis of pottery from SM14 showed consistent composition, indicating production used standardized materials and techniques, evidence of craft specialization and quality control. A different pattern emerged at site SM23, located 21 kilometers northwest of Landivar. Here, excavations revealed specialized fish processing facilities. The site sat adjacent to a permanent water body, one of the oxbow lakes that dotted the region. Excavation units yielded extraordinary quantities of fish remains, with bone concentrations exceeding 10,000 specimens per cubic meter of deposit. Species analysis showed that over 80% of the fish remains came from just 3 species. all large fish that provided substantial meat yields. This concentration suggested selective fishing rather than opportunistic capture of whatever was available. The processing facilities included what appeared to be smoking racks, linear arrangements of post holes where fish could have been hung for preservation. The economic specialization of these satellite sites indicated a sophisticated regional organization where different communities produced specific goods for exchange within the broader network. The forest islands, scattered throughout the flooded savannas of the Llanos de Moxos, are forest islands, patches of dense vegetation rising above the surrounding grasslands. For decades, ecologists assumed these were natural features, perhaps representing areas of slightly higher elevation that remained above water during seasonal floods, allowing trees to establish. But archaeological surveys conducted between 2015 and 2023 revealed that many of these forest islands were actually artificial, created by ancient inhabitants as elevated habitation sites during flood seasons. Excavations showed these islands contained deep cultural deposits with stratified layers of occupation, debris, pottery, and food remains extending back over 1,000 years. The islands weren't just occupation sites but were actively managed landscapes. Soil samples showed that inhabitants had deliberately enriched the earth with organic matter and charcoal, creating terra preta soils. They had also selectively planted useful tree species, creating forest gardens that continued to produce food centuries after abandonment. The Forest Island investigation began with a simple observation. Aerial photographs showed that these patches of forest weren't randomly distributed, but appeared in clusters and linear arrangements that suggested human agency. Dr. Umberto Lombardo from the University of Bern initiated a systematic survey documenting the location, size, and vegetation composition of 342 forest islands across an 8,000 square kilometre study area. The survey revealed patterns inconsistent with natural formation. Natural high ground in the Llanos de Moxos tends to be elongated, following ancient river levees or geological ridges, but the forest islands were predominantly circular or oval, with diameters ranging from 50 to 300 metres. Their elevations, measured using differential GPS, showed they rose 1 to 4 metres above the surrounding savanna, just enough to remain above flood levels during typical wet seasons. Test excavations at 12 forest islands revealed their anthropogenic origins. Each excavation encountered similar stratigraphic sequences. At the bottom, typically 2 to 3 metres below the surface, lay natural subsoil yellowish clay with no cultural materials. Above this, cultural deposits began dark soil mixed with charcoal, pottery fragments, bone, and other occupation debris. These cultural deposits ranged from 1 to 2.5 metres thick, indicating centuries of accumulation. The radiocarbon chronology showed that many forest islands had been occupied for extended periods. At one site, organic materials from the lowest cultural layer dated to 490 AD, while materials from near the surface dated to 1000. 320 AD, indicating nearly 900 years of continuous or repeated occupation. The deposits weren't uniform but showed distinct layers separated by sterile or less artifact-rich zones, suggesting pulses of intensive use alternating with abandonment or reduced activity. The soil chemistry revealed intentional modification. Terra preta deposits on the forest islands contain charcoal at concentrations of 15 to 25% by weight, far higher than typical Amazonian soils. Phosphorus levels reached 800 to 1,200 parts per million, compared to background levels of less than 100 parts per million. These elevated values indicated deliberate addition of organic waste, bone, and other materials that enriched the soil, while also gradually raising the island's elevation. The vegetation on forest islands differed markedly from surrounding areas. Botanical surveys documented 45 to 60 tree species on each island, compared to only 8 to 12 species in the surrounding savanna. More significantly, the forest island vegetation was dominated by useful species. Brazil nut trees appeared on 73% of surveyed islands. Various palm species used for construction and food occurred at high densities. Fruit trees, including cacao and several Inga species, were present on over half the islands. This species composition couldn't be explained by natural dispersal. Statistical analysis showed that useful species occurred at frequencies 5 to 15 times higher than would be expected if seeds had arrived through random processes like wind, water, or animal dispersal. The pattern indicated deliberate planting and maintenance of forest gardens that persisted centuries after human management ceased. The ceramic evidence. Pottery styles provide archaeologists with some of their most reliable methods for tracking cultural changes and connections over time. Analysis of thousands of ceramic sherds from Kasara Bay sites revealed several distinct pottery traditions, each with characteristic decorative styles, vessel forms, and manufacturing techniques. But in 2020, researchers using a technique called ceramic petrography, the microscopic analysis of the mineral inclusions in pottery, made a surprising discovery. Many vessels found at different Kasara Bay sites were not just stylistically similar, but were made from identical clay sources, indicating they were manufactured at centralized production facilities and then distributed across the region. This evidence of specialized ceramic production and distribution suggested economic organization that went beyond local craft production. Kilometers. The ceramic petrography study was conducted by Dr. Jennifer Loffmiller Cardinal from the University of Wyoming. She collected samples from 287 pottery vessels, recovered from excavations at 15 different Kasara Bay sites. From each vessel, she extracted a small fragment, typically 1 cubic centimeter, which was then processed into a thin section for microscopic analysis. The thin sectioning process involved embedding the pottery fragment in epoxy resin, then cutting and grinding it to a thickness of 30 micrometers, thin enough for light to pass through. Mounted on glass slides, these thin sections revealed the pottery's internal structure when examined under polarized light microscopy. The mineral inclusions, sand grains, rock fragments, and other particles mixed into the clay became clearly visible, each mineral identifiable by its distinctive optical properties. The analysis revealed that Kasara Bay pottery contained diverse mineral inclusions, including quartz, feldspar, volcanic rock fragments, and various metamorphic minerals, but the specific combinations varied systematically. Dr. Loffmiller Cardinal identified 7 distinct fabric groups, pottery types with characteristic mineral assemblages, indicating they were made from different clay sources. The geographic distribution of these fabric groups revealed production and exchange patterns. Fabric Group A, characterized by abundant volcanic rock fragments, appeared in vessels from 12 of the 15 sites. Chemical analysis using neutron activation traced this fabric's clay source to an area near Kotoka, suggesting the major urban center was home to specialized pottery workshops that distributed their products across the region. Fabric Group C, containing distinctive metamorphic minerals, appeared only at sites in the northern part of the Kasara Bay region. The clay source for this group lay near one of the secondary centers, suggesting regional production and more localized distribution networks. The most intriguing finding involved high-quality serving vessels, bowls and plates with fine walls and elaborate painted decoration. Over 80% of these elite vessels belonged to Fabric Group A, the Kotoka source pottery. This suggested that elite pottery production was centralized at the major urban center, with these prestige items distributed to secondary sites where local elites used them in ceremonies and feasts. The distribution mechanism remained unclear. Were the pots traded as commodities? Were they gifts distributed by Kotoka leaders to allies and subordinates? Or were they moved through tribute systems where secondary sites sent goods to the center and received pottery in return? The archaeological evidence couldn't definitively answer these questions, but the pattern indicated economic integration transcending individual settlement boundaries. The sudden abandonment. One of the most haunting aspects of Kasara Bay archaeology is evidence of sudden abandonment. At several sites, excavations have uncovered buildings that appear to have been left intact. Pottery vessels still on floors, tools lying where they were last used, construction projects abandoned mid-work. Radiocarbon dating of the final occupation layers across multiple sites suggests this abandonment occurred within a relatively brief period, possibly within a single generation around 1400 AD. But there's no evidence of warfare or violent destruction. No burned buildings, no mass graves, no signs of invasion or conflict. The cities were simply left empty. Where did the population go? The genetic evidence suggests they didn't disappear. They dispersed. Modern indigenous populations in the region carry genetic markers, linking them to the Kasara Bay culture, indicating the people survived but abandoned their urban lifestyle, reverting to smaller-scale settlements scattered throughout the forest. The abandonment evidence was first recognized at a site called Loma Suarez during excavations in 2017. The team uncovered a residential structure on a low platform mound, its post holes still clearly defined, and artifacts lying on the floor surface exactly where they had been when the building was abandoned. A ceramic storage jar sat in one corner, still containing charred maize kernels. Stone tools lay scattered near what appeared to have been a work area. A grinding stone with another stone resting on top sat as though someone had been in the middle of processing food when they stopped. The lack of disturbance was significant. When buildings are abandoned gradually, occupants typically remove valuable items, salvage useful materials, and leave behind only broken or worthless objects. But at Loma Suarez, complete vessels, functional tools, and valuable goods remained in place. This suggested rapid departure, people leaving quickly without time to gather their possessions. Similar patterns appeared at other sites. At Landivar, excavations uncovered an unfinished causeway extension. The earthwork had been partially built, with fill material piled but not yet shaped or surfaced. The construction had simply stopped midway, with no evidence of later attempts to complete or salvage the work. At another site, excavators found a partially completed platform mound, its construction layers clearly visible where work had ceased before the structure reached its intended height. The radiocarbon dating provided the temporal framework for understanding this abandonment. By dating organic materials from the final occupation surfaces at multiple sites, researchers established that the abandonment wasn't instantaneous, but occurred over a period of approximately 50 to 80 years, centered on 1400 AD. Kotoka showed final occupation dates around 1410 AD. Landivar's latest dates clustered around 1390 AD. Smaller sites showed abandonment dates ranging from 1380 to 1450 AD. This timeline suggested a gradual but relatively rapid collapse. Over 2 or 3 generations, the population left the urban centers and their satellite settlements, dispersing into the surrounding landscape. The genetic evidence confirmed they didn't vanish entirely. DNA analysis of modern indigenous populations showed clear genetic continuity with pre-Columbian populations, indicating the people survived the collapse and remained in the region. The lack of violence was puzzling. In many cases of civilizational collapse, the fall of Mycenaean Greece, the end of the classic Maya, the abandonment of Cahokia archaeology reveals evidence of warfare, destruction, and social conflict. But Kasarabi sites showed no such evidence. No burned structures, no bodies bearing trauma, no caches of weapons, no defensive walls hastily erected against threats. This suggested the abandonment was coordinated rather than forced. Perhaps religious or political leaders decided to abandon the urban centers, directing populations to disperse. Perhaps environmental changes made the intensive agricultural systems unsustainable, forcing a return to more mobile subsistence strategies. Or perhaps disease, possibly indigenous diseases, spread through densely populated urban centers caused enough mortality that the remaining population couldn't maintain the infrastructure and organization required for urban life. The astronomical alignments. Archaeoastronomers studying the layout of Kasarabe settlements have identified numerous alignments between architectural features and celestial events. At several sites, the major causeways are oriented within 2 degrees of true north-south or east-west, a precision that requires astronomical observation. More specifically, at one site called Loma Mendoza, researchers discovered that sight lines between platform mounds aligned with the sunrise position on the summer solstice and the setting position of the Pleiades star cluster. These alignments weren't coincidental. Computer modeling showed the probability of such precise alignments occurring by chance was less than 1 inch. 10,000. The astronomical orientation suggested that Kasarabe architects incorporated celestial observations into their urban planning, possibly linking their physical cities to cosmic geography in ways that reflected their cosmological beliefs. The archaeoastronomy study was led by Dr. Stephen Gullberg from the University of Oklahoma. His team used high-precision GPS equipment to map the locations of major architectural features at 5 Kasarabe sites, then used astronomical software to calculate the positions of celestial objects as they would have appeared between 800 and 1400 AD, accounting for the precession of Earth's axis over the intervening centuries. At Loma Mendoza, The analysis revealed multiple significant alignments. The site's main causeway ran almost exactly east-west, deviating only 1.3 degrees from true cardinal alignment. This precision alone suggested astronomical orientation. The causeway's eastern terminus aligned with the sunrise position on the spring and fall equinoxes, the 2 days each year when the sun rises directly in the east. More specific alignments appeared in the relationships between platform mounds. Loma Mendoza featured 3 major mounds arranged in a triangular pattern. Sightlines between these mounds showed astronomical significance. Looking from Mound A toward Mound B, the alignment pointed to the sunrise position on the winter solstice, the shortest day of the year, marking an astronomically significant moment. Looking from Mound A toward Mound C, the alignment matched the setting position of the Pleiades star cluster, as it appeared around 1100 AD. The Pleiades alignment was particularly interesting because this star cluster held significance for many Amazonian cultures. Modern indigenous groups used the Pleiades' first visible rising after a period of invisibility to mark the beginning of the rainy season. The archaeological evidence suggested this calendrical use had ancient roots, with the Kasarabe people incorporating Pleiades observations into their architectural planning. Statistical analysis tested whether these alignments could be coincidental. Dr. Gullberg's team used Monte Carlo simulation, generating 10,000 random arrangements of 3 mounds and calculating how often these random arrangements produced alignments within 2 degrees of significant astronomical positions. The simulation showed that only 0.08% of random arrangements fewer than 1 inch 1000 produced alignments as precise as those observed at Loma Mendoza. This statistical result strongly supported intentional astronomical orientation. Similar patterns appeared at other sites. Kotoka's main platform mound had its longest axis oriented 2.7 degrees from true north, with the structure's corners aligned to the 4 cardinal directions. The causeway connecting Kotoka and Landivar ran almost perfectly east-west, suggesting both sites were positioned to maintain this astronomical alignment. The astronomical alignments implied sophisticated observational astronomy. Creating cardinal alignments requires determining true north, which can be done by observing the star's circular motion around the celestial pole. Solstice alignments require tracking the sun's rising or setting position over extended periods to identify the extreme positions marking the year's longest and shortest days. These observations required dedicated skywatchers with knowledge passed down across generations. The cosmological implications extended beyond practical calendrical functions. By aligning their cities with celestial phenomena, the Kasarabe people were embedding cosmological meaning into their built environment. The physical layout of their settlements reflected and reinforced beliefs about the relationship between earthly and celestial realms, creating spaces where human activities connected with cosmic cycles. The bone chemistry, secrets, isotope analysis of human remains from Kasarabe sites has revealed unexpected details about ancient diets and lifestyles. By measuring the ratios of carbon and nitrogen isotopes in bone collagen, researchers can reconstruct the types of foods individuals ate during their lifetimes. The analysis showed that Kasarabe populations had remarkably diverse diets, incorporating fish, maize, manioc, and wild game in varying proportions. But the isotope ratios also revealed something unexpected: significant dietary differences between individuals buried in elaborate tombs on platform mounds and those buried in simpler graves in residential areas. Elite individuals showed higher consumption of maize and fish, while common people relied more heavily on manioc. This dietary stratification provides some of the clearest evidence for social hierarchy in Kasarabe society, suggesting that access to certain foods was restricted based on social status. The isotopic analysis was conducted by Dr. Amanda Logan from Northwestern University. She collected bone samples from 73 individuals buried at 4 different Kasarabe sites. The sampling focused on ribs and long bones, which preserve collagen well and represent dietary intake averaged over several years before death. The laboratory analysis measured stable isotope ratios of carbon and nitrogen. Carbon isotopes distinguish between different types of plants. C3 plants like manioc and most trees have lower delta 1,3C values, while C4 plants like maize have higher values. Nitrogen isotopes indicate trophic level. Fish and meat consumers show higher delta-15N values than those eating primarily plant-based diets. The results revealed striking patterns. Individuals buried on platform mounds in elaborate tombs showed delta-13C values averaging negative 15.2, consistent with diets where 40–50% of calories came from maize. Their delta-15N values averaged 11.8, indicating substantial fish and meat consumption. In contrast, individuals buried in simple graves in residential areas showed delta-13C values averaging negative 18.7, consistent with diets where only 15–20% of calories came from maize, with manioc providing the majority. Their delta-15N values averaged 9.2, indicating lower animal protein intake. These differences were statistically significant and socially meaningful. Maize required more labor to cultivate than manioc, and produced impressive displays when stored in large quantities. Fish required specialized equipment and knowledge to capture efficiently. The dietary patterns suggested that elite individuals consumed prestige foods that proclaimed their status, while commoners relied on more basic staples. The isotope data also revealed childhood dietary patterns through analysis of tooth enamel, which forms during youth and preserves a record of childhood diet. Several elite adults showed isotope values in tooth enamel similar to common individuals, then showed elevated values in bone collagen representing adult diet. This suggested social mobility. Individuals born into common families who achieved elite status as adults and gained access to elite foods. Geographic variation appeared in the isotope data. Individuals from sites near permanent water bodies showed higher fish consumption than those from sites more distant from water. Sites in the northern Kasarabe region showed slightly higher reliance on wild game, while southern sites showed more intensive maize cultivation. These patterns reflected local environmental conditions and economic specializations. The experimental archaeology, understanding how ancient technologies worked, often requires trying to recreate them. In 2018, a team of experimental archaeologists attempted to build a scaled-down replica of a Kasarabe platform mound, using only tools and techniques available to the original builders. The project took 3 months and involved 30 participants working with stone axes, wooden spades, and woven baskets for transporting earth. The experiment revealed several insights into ancient construction methods. First, the work went faster than expected. The team calculated that a full-scale mound could have been built by a workforce of 500 people in approximately 3 years, far less than previous estimates. Second, the builders discovered that the layered construction technique wasn't just for stability, it also served as a form of quality control, allowing architects to check the platform's level and make adjustments at each layer. The experimental construction project was organized by Dr. Clark Erickson from the University of Pennsylvania, who had decades of experience studying Amazonian earthworks. The team selected a location near a Kasarabe site, using soil conditions similar to those the ancient builders would have encountered. The replica platform was designed at 1:10 scale, a structure 3 meters high, 20 meters long, and 15 meters wide, which would scale to a 30-meter high full-size platform. Tool replication was crucial. Archaeologists commissioned 40 stone axes, crafted by a skilled napper using traditional techniques. The axes were hafted to wooden handles using fiber bindings and plant-based adhesives. Wooden digging implements were carved from hardwood, with fire-hardened points. Baskets for carrying earth were woven from local plant fibers in patterns matching archaeological examples. The project began with soil excavation. Teams of 4 workers dug earth from designated borrow pits located 50 meters from the construction site. They used stone axes to break up soil and roots, then scooped loosened earth into baskets. Each basket held approximately 20 liters of earth and weighed 30 to 35 kilograms when full. Workers carried loaded baskets to the construction site and dumped them at designated locations. The work rate was carefully documented. Each team's output was measured by counting basket loads and recording time. The average team moved 2.5 cubic meters of earth per 8-hour workday, higher than previous estimates had suggested. Scaled to full-size construction, this meant that 500 workers could move 1,250 cubic meters per day, completing a 500,000 cubic meter platform in 400 working days. The layered construction technique proved essential for maintaining quality, rather than simply piling earth. Builders spread each load into thin layers, approximately 20 centimeters thick, then compacted these layers by walking on them. After completing each layer across the entire platform area, the team used water-filled tubes, a simple level based on the principle that water seeks its own level, to check that the surface was horizontal. This allowed corrections before adding the next layer. The experiment revealed organizational requirements. Coordinating 30 workers required constant communication and planning. Different teams needed to work in sequence. Excavators filled baskets, carriers transported them, and placement crews spread and compacted earth. Scaled to 500 workers, this organizational complexity would require supervisors, specialized work crews, and systematic procedures that ancient Kasarab societies had apparently developed. The physical demands were substantial. After 8 hours of digging and carrying earth, participants were exhausted. The experiment suggested that full-time workers couldn't maintain this pace indefinitely. More likely, ancient construction involved larger numbers of people working in shorter shifts, or working only during seasons when agricultural demands were lower. The project demonstrated that monumental architecture required not just engineering knowledge but sophisticated labor organization. The ring ditch enigma. Among the most mysterious features identified in LiDAR surveys are ring ditches, circular or oval depressions, typically 40 to 100 meters in diameter, found scattered across the Kasarabe landscape. Unlike the platform mounds, which clearly served as foundations for buildings, the function of these ring ditches remained unclear. Excavations of several examples found no evidence of structures within the enclosed areas. The ditches themselves were relatively shallow, 2 to 3 meters deep, and showed no signs of having been filled with water for defensive purposes. In 2022, archaeologists from the University of Exeter proposed a new interpretation based on ethnographic analogies. They suggested the ring ditches might have served as corrals for managing semi-domesticated animals, possibly peccaries or even capybaras, which could have been important protein sources. Excavations, specifically targeting these features, in 2023 found elevated levels of phosphorus in the enclosed areas, chemical evidence consistent with animal management, lending support to this interpretation. The ring ditch investigation began with systematic documentation using LiDAR data. Researchers identified 186 ring ditches across the Kasarabe region, mapping their locations, sizes, and spatial relationships. The features showed consistent characteristics, circular or slightly oval shapes, diameters of 40 to 120 meters, and ditches approximately 2 to 4 meters wide. The distribution pattern was intriguing. Ring ditches appeared primarily near residential areas, rather than clustered around ceremonial centers. Most were located within 500 meters of platform mounds or other occupation features, suggesting they served domestic rather than ceremonial functions. Dr. Jose Capriles from Pennsylvania State University led the excavation program. His team selected 6 ring ditches for intensive investigation, excavating cross-sections through the ditches and test units within the enclosed areas. The ditch profiles were consistent shallow excavations with sloping sides and flat bottoms, showing no evidence of having been lined with clay or other waterproofing materials. The enclosed areas yielded sparse artifacts. Pottery fragments appeared in low densities, without the concentrations typical of residential areas. Stone tools were rare. The paucity of occupation debris suggested these spaces weren't used for housing or intensive activities that would leave archaeological traces. The breakthrough came from soil chemistry. Samples collected from within ring ditch enclosures showed phosphorus levels averaging 450 parts per million, compared to 120 parts per million in nearby areas outside the ditches. Elevated phosphorus typically indicates organic waste accumulation, particularly from animal manure and urine. The faunal evidence provided additional support. Though animal bones appeared in low quantities, species composition was revealing. Over 60% of identified bones came from peccaries, medium-sized pig-like animals native to South America. Modern peccaries are typically hunted wild, but ethnographic accounts describe some Amazonian groups keeping young peccaries as semi-domesticated animals. The ring ditch configuration would have been suitable for containing animals. The shallow ditches wouldn't prevent escape, but would discourage it, particularly for young animals. Ethnographic parallels showed that Amazonian groups sometimes kept wildlife in loose confinement, allowing animals to forage within enclosed areas while preventing them from wandering too far. The hypothesis remained tentative. Direct evidence of animal management, such as modified bones from butchery or specialized feeding installations, was absent. But the combination of elevated phosphorus, peccary bone concentrations, and suitable enclosure design created a plausible case that ring ditches served animal management functions, representing an intermediate stage between hunting and full domestication. The lost language, unlike the Inca, who used quipus knotted strings for record-keeping, or the Maya with their sophisticated hieroglyphic script, no writing system has been definitively identified for Kasarabe culture. But that doesn't mean they lacked methods of information storage. In 2020, researchers examining geometric patterns carved into ceramic vessels noticed something intriguing. Many of the patterns showed systematic variations that seemed too consistent to be purely decorative. Statistical analysis of these patterns revealed they followed specific rules, with certain motifs appearing in predictable combinations. This suggested the patterns might represent a form of proto-writing or symbolic notation system, possibly used for recording information about trade, tribute, or ritual obligations. The investigation was led by Dr. Catherine Josserand, a linguist and iconography specialist from Florida State University. She photographed and catalogued decorative patterns from 412 ceramic vessels recovered from 8 Kasarabe sites. The vessels included bowls, jars, and plates spanning the entire Kasarabe chronological sequence from 500 to 1400 AD. Initial analysis identified 34 distinct motifs that appeared repeatedly. These included geometric designs like cross-hatching, spirals, zigzags, and concentric circles, as well as more representational elements depicting animals, human figures, and plants. What caught researchers' attention was that these motifs didn't appear randomly, but showed consistent patterns of association. Statistical analysis tested for non-random patterning. Dr. Josserand coded each vessel's decorative program. The sequence and combination of motifs then used cluster analysis to identify patterns. The analysis revealed that certain motifs co-occurred significantly more often than chance would predict. For example, spiral motifs appeared with zigzag patterns in 67% of cases where spirals occurred, far exceeding the 23% expected frequency if combinations were random. The patterns suggested rule-governed combination. Certain motifs went together in ways determined by systematic principles rather than individual artistic choice. This was consistent with symbolic notation systems, where signs combine according to conventional rules to convey specific meanings. Further analysis examined motif sequences. On vessels where decorative patterns formed clear linear arrangements, researchers documented the order of motifs from left to right. The analysis revealed that certain motifs appeared primarily in initial positions, others in terminal positions, and still others in medial positions, similar to how writing systems have signs that occur mainly at word beginnings or endings. Chronological analysis showed the system evolved over time. Vessels from the early period, 500 to 800 AD, showed 12 distinct motifs in relatively simple combinations. Later vessels, 1000, 100 to 1400 AD, employed 29 motifs in increasingly complex arrangements, suggesting the system was becoming more elaborate and possibly more information-rich. The hypothesis remained speculative. Without a Rosetta Stone, a text that appears in both the unknown system and a known language decipherment was impossible. But the patterns provided tantalizing hints that Kasarabe culture had developed a system for encoding information visually, a technology that fell somewhere between purely decorative art and full writing. The Water Temple discovery. In 2019, excavations at a Kasarabe site near the Rio Blanco uncovered a structure unlike any previously found. Built partially into the bank of an ancient reservoir, the structure featured a subterranean chamber accessed by a stone-lined staircase that descended 8 meters below the surrounding ground level. The chamber was precisely constructed, with walls made from carefully selected stones and a floor paved with fired clay. At the chamber's center was a basin with channels that would have allowed water to flow in from the reservoir. Ceramic offerings and the remains of what appeared to be ritual meals surrounded the basin. The excavators interpreted the structure as a water temple, a sacred space where rituals relating to water control and agricultural fertility would have been performed. The temple's location at the heart of the water management system suggested that Kasarabi religion and engineering were intimately connected, with the control of water seen as both a technical and a sacred duty. The discovery occurred during excavations led by Dr. Heiko Prumers from the German Archaeological Institute. The team had been investigating a platform mound adjacent to a large reservoir when ground-penetrating radar detected an anomaly, a void beneath the ground surface near the reservoir's edge. Initial test excavations revealed the top of a stone staircase, prompting a full-scale investigation. The staircase was remarkably well preserved. 23 stone steps descended at a consistent angle of 32 degrees, each step carved from a single block of sandstone measuring approximately 80 centimeters wide. The sides of the staircase were lined with vertical stone slabs, creating walls that prevented soil from collapsing into the passage. At the bottom, the staircase opened into a rectangular chamber measuring 6 meters long, 4 meters wide, and 2.8 meters high. The chamber walls showed sophisticated construction. Rather than rough field stones, the builders had used carefully selected flat stones, some showing evidence of shaping through pecking and grinding. The stones were laid in regular courses, each layer offset from the one below to create a stable interlocking structure. No mortar was used, but the tight fitting of the stones created a solid wall that had survived over 600 years underground. The floor consisted of fired clay tiles similar to those found in the underground canal systems. The tiles formed a continuous surface, sloping gently toward a central basin, a circular depression, approximately 1.5 meters in diameter and 40 centimeters deep. The basin's edges showed polishing from water flow, indicating it had been actively used. 2 channels, each about 15 centimeters wide, led from the basin toward the reservoir, suggesting water could be directed in or out of the chamber. The artifactual evidence revealed the chamber's ceremonial function. Arranged around the basin were 23 complete ceramic vessels, mostly bowls and jars with elaborate painted decoration. Unlike typical domestic pottery that showed useware from cooking and storage, these vessels appeared pristine, purpose-made for ritual deposition. Chemical analysis detected cacao residues in several vessels, consistent with ceremonial beverage consumption. Animal bones scattered around the basin represented at least 7 individual animals, 4 fish, 2 birds, and 1 mammal tentatively identified as a peccary. The bones showed cut marks from butchery but no signs of burning, suggesting the animals had been ritually sacrificed and possibly consumed raw or minimally processed. The species selection, all aquatic or semi-aquatic animals, reinforced the water theme. Most intriguingly, carved into one wall near the basin was a relief depicting a human figure with arms raised, water flowing from its hands. The iconography clearly connected human agency with water control, suggesting the temple served as a space where ritual actions were believed to influence the hydraulic systems that sustained Kasarabe agriculture. The integration of religion and engineering reflected a worldview where technical and spiritual domains were inseparable. The population collapse. Recent attempts to estimate the population of Kasarabe civilization at its peak have produced staggering numbers. By calculating the density of residential structures identified in LiDAR surveys, and comparing this with ethnographic data on family sizes and house occupancy rates, researchers estimate that the 2 major urban centers housed between 10,000 and 15,000 people each. The surrounding satellite settlements may have added another 15,000 to 20,000 to the regional population. These numbers would make the Kasarabe region one of the most densely populated areas in pre-Columbian South America, rivaling contemporaneous civilizations in Mesoamerica. Yet by 1500 AD, when Europeans first reached the region, this population had disappeared. Genetic and archaeological evidence suggests the collapse may have reduced regional populations by 80% or more. But with no clear cause, the population estimates relied on multiple lines of evidence. LiDAR surveys identified over 2,400 residential structures across the Kasarabe core region, rectangular depressions indicating house foundations, excavations of 37. Such structures provided data on average house size, approximately 35 square meters, and household composition. Archaeological evidence suggested nuclear or small extended families, averaging 5 to 7 individuals per household. At Kotoka, LiDAR identified 847 residential structures, distributed across the site's 147 hectares. If each housed 6 people on average, the population would have reached approximately 5,100. But not all structures would have been occupied simultaneously. Some were abandoned as new ones were built. Archaeologists estimated 60% occupancy at any given time, suggesting a population around 3,000 for Kotoka alone. However, additional residential areas in the site's periphery, where structures were less clearly visible in LiDAR data, could have pushed the total to 10,000 or higher. Similar calculations for Landivar suggested populations of 8,000 to 12,000. The 24 secondary centres, with populations estimated at 500 to 2,000 each, added another 15,000 to 25,000. The numerous small sites contributed additional thousands. The total regional population at peak prosperity may have reached 40,000 to 60,000, extraordinary for a pre-industrial society in the Amazon environment. The collapse evidence was stark. By 1500 AD, Spanish chronicles described scattered indigenous populations in the region, but made no mention of substantial settlements. Population estimates for the early colonial period suggest indigenous populations in the Llanos de Moxos numbered fewer than 10,000, an 80 to 90% reduction from pre-Columbian peaks. The causes remain debated. Environmental explanations pointed to drought, flooding, or soil exhaustion. Social explanations suggested warfare, political fragmentation, or the breakdown of trade networks. Disease explanations proposed epidemics, either indigenous diseases spreading through dense urban populations or European diseases arriving ahead of direct contact through indigenous trade networks. The genetic bottleneck detected in modern populations supported the disease hypothesis. Molecular clock analyses suggested the bottleneck occurred around 1,400 to 1,500 AD, consistent with the timing of collapse. Population reductions severe enough to create such genetic signatures typically result from catastrophic mortality events like epidemics rather than gradual decline. The dispersal pattern suggested organized abandonment rather than death in place. If disease or famine killed the population, archaeologists would expect to find mass graves or scattered remains. Instead, sites showed evidence of orderly departure buildings left intact, minimal human remains, no signs of catastrophe. The population apparently made a deliberate decision to abandon urban centres and return to dispersed settlement patterns. The jungle's memory. Modern ecological studies have revealed that the Amazon rainforest itself preserves a record of past human occupation. Researchers cataloguing tree species in areas near archaeological sites have found that the forest composition differs significantly from more distant areas. Species useful to humans, fruit trees, palms, and trees with medicinal properties are far more abundant near ancient settlements, even centuries after abandonment. Soil scientists have shown that terra preta deposits continue to influence vegetation patterns, with plants growing in anthropogenic soils showing different growth rates and flowering times than those in unmodified forest soils. In some areas, the layout of ancient settlements can still be detected in the modern forest canopy, with different tree species growing along former roads and causeways. The forest has recovered, but it hasn't forgotten the human past is written into the landscape in ways that persist across centuries. Dr. Charles Clement from Brazil's National Institute for Amazonian Research led the botanical investigation. His team conducted transect surveys through forest areas within 5 kilometers of known archaeological sites, documenting every tree with trunk diameter exceeding 10 centimeters. Over 3 field seasons, they recorded 12,847 individual trees representing 342 species. The analysis revealed striking patterns. Within 500 meters of archaeological sites, useful tree species comprised 28% of documented individuals, compared to only 11% in areas more than 2 kilometers from sites. Brazil nut trees showed the most dramatic concentration, occurring at densities of 12 to 18 trees per hectare near sites versus 2 to 4 trees per hectare in distant areas. Palms useful for construction and food showed similar patterns, with 3 to 5 times higher densities near ancient settlements. The species composition near archaeological sites also showed lower diversity in some ways, but higher in others. Dominant canopy species, typical of undisturbed forest, were less common, while useful understory and mid-canopy species appeared more frequently. This suggested ancient inhabitants had actively managed forest composition. removing some trees to favor useful species, a practice still observed in some contemporary indigenous communities. Soil chemistry explained some patterns. Vegetation surveys correlated with soil testing showed that trees growing in terra preta soils exhibited different characteristics. Growth rates, measured through increment cores, showed that trees in anthropogenic soils grew 15 to 25% faster than the same species in unmodified soils. Leaf nutrient content was higher, and seed production was more abundant. The enriched soils provided lasting competitive advantages to trees growing in them. Most remarkably, satellite imagery analysis revealed that ancient settlement patterns could sometimes be detected in modern forest structure. Multispectral images captured differences in canopy height, vegetation density, and leaf chemistry that corresponded to archaeological features. Former causeways appeared as linear features where tree composition differed from surrounding areas. Platform mounds showed as subtle circular patterns in canopy structure. The forest had grown over these features, but vegetation responded to the modified soils and topography beneath, preserving the ancient landscape in subtle ways. The findings challenged concepts of pristine wilderness. Ecologists had long assumed that some Amazon regions were untouched by human influence, representing baseline natural conditions. But the botanical evidence suggested human influence extended far more widely than visible archaeological sites indicated. Even areas that appeared to be undisturbed old-growth forest might actually be recovering human-modified landscapes. Their species composition still reflecting management that ceased centuries ago. The disease theory, the most widely accepted explanation for the collapse of Amazonian civilizations, involves epidemic disease introduced by European contact. Historical accounts document devastating epidemics sweeping through indigenous populations in the decades following Columbus's arrival in the Americas. Diseases like smallpox, measles, and influenza, to which Native Americans had no immunity, could kill 80–90% of affected populations. But there's a troubling gap in this narrative. The archaeological evidence suggests Kasarabe civilization collapsed around 1400 AD, decades before Columbus reached the Americas in 1492. Some researchers have proposed that diseases might have spread into the Amazon interior through indigenous trade networks before any direct European contact, carried by coastal populations first exposed to European diseases. Others suggest the collapse might have had indigenous causes, perhaps an epidemic of a native disease or a cascade of environmental and social factors that weakened the civilization before European contact delivered the final blow. The disease hypothesis gained support from comparative evidence. Similar demographic catastrophes occurred throughout the Americas, following European contact. In central Mexico, the indigenous population declined from approximately 25 million in 1519 to 1 million by 1600, a 96% reduction. Caribbean island populations virtually disappeared within 50 years of Columbus's arrival. The pattern was consistent across diverse environments and cultures, suggesting a common cause: epidemic disease. The mechanism was well understood. Native American populations had been isolated from Eurasian disease pools for over 10,000 years, since their ancestors crossed from Siberia into North America. During this isolation, they never encountered diseases like smallpox, measles, typhus, and influenza that had evolved in Eurasian populations living in close contact with domesticated animals. When these diseases arrived with European contact, Native Americans had no genetic resistance or acquired immunity. Mortality rates in virgin soil epidemics, diseases striking populations with no prior exposure, could exceed 90%. But the timing problem remained. How could European diseases cause a collapse that occurred before Europeans arrived? One hypothesis proposed that diseases spread faster than Europeans themselves. Coastal populations contacted in the 1492 and early 1500s could have transmitted diseases to interior populations through trade networks. Diseases could travel hundreds of kilometers ahead of Europeans, carried by indigenous traders who survived infection and became asymptomatic carriers. Computer modeling tested this hypothesis. Epidemiological simulations, using parameters derived from historical epidemic data, showed that diseases with long incubation periods and the possibility of asymptomatic transmission could indeed spread rapidly through connected populations. Starting from initial infections on the Caribbean coast around 1500, simulations showed diseases could reach the Bolivian interior by 1520 to 1530, still too late to explain the 1400 collapse, but possibly contributing to later population declines. Alternative explanations focused on indigenous diseases. Skeletal evidence from Casarabe sites showed that pre-Columbian populations suffered from various health problems, including parasitic infections, dental diseases, and traumatic injuries. Perhaps an endemic disease, one normally present at low levels, underwent a mutation or found favorable conditions that allowed it to become epidemic. Tuberculosis, for example, was present in pre-Columbian Americas and could cause mortality spikes under conditions of malnutrition and crowding. The cascade hypothesis suggested multiple stresses combined to cause collapse. Environmental stress from drought or flooding reduced food production. Malnutrition weakened immune systems, making populations more susceptible to disease. Disease reduced labor forces, preventing maintenance of agricultural infrastructure. Agricultural collapse led to famine. Social breakdown followed demographic collapse. No single cause was responsible. Rather, multiple factors reinforced each other in a downward spiral. The evidence remained circumstantial. Without ancient DNA from pathogens, which rarely preserves in tropical environments, identifying specific diseases was impossible. The collapse remained a mystery with plausible explanations, but no definitive proof. The modern discovery methods, the technology revolutionizing Amazonian archaeology, continues to advance. In 2023, researchers began using a new generation of LiDAR sensors mounted on drones, allowing detailed scanning of small areas with resolution, measuring individual stones and features smaller than 10 centimeters. Multispectral satellite imaging, which captures light beyond the visible spectrum, can detect subtle changes in vegetation that indicate buried structures. Machine learning algorithms trained on known archaeological sites can now automatically identify potential new sites in satellite imagery, a process that has accelerated the rate of discovery dramatically. In 2024 alone, over 60 previously unknown sites were identified using these automated methods in regions that had previously been surveyed using traditional ground methods. Each new site adds pieces to the puzzle, gradually revealing the full scale of pre-Columbian Amazonian civilization. The drone-based LiDAR systems represented a significant advance over aircraft-mounted sensors. Drones could fly at altitudes of 50 to 100 meters, much lower than aircraft, allowing for extreme resolution. The latest sensors captured over 500 points per square meter, revealing details like individual stones, small depressions, and subtle earthworks invisible to earlier systems. The drones could also fly below cloud cover and navigate around obstacles, providing flexibility impossible with fixed-wing aircraft. Dr. Albert Lin from the University of California, San Diego pioneered the use of drone LiDAR in the Amazon. His team deployed hexacopter drones equipped with lightweight LiDAR sensors weighing less than 2 kilograms. The drones flew automated grid patterns controlled by GPS, scanning areas of 50 to 100 hectares per day. The resulting data was processed using photogrammetry software to create ultra-high-resolution digital terrain models. The detail level was extraordinary. At one Casarabe site, drone LiDAR revealed individual stones in building foundations, allowing archaeologists to map structure plans without excavation. Small features like post holes, hearths, and refuse pits appeared clearly in the data. Multispectral satellite imaging added another dimension. Satellites like WorldView 3 and Sentinel-2 captured imagery in multiple wavelengths, including visible light, near-infrared, and shortwave infrared. Different wavelengths revealed different features. Near-infrared detected variations in vegetation health. Plants growing in anthropogenic soils showed different chlorophyll content and leaf structure than those in natural soils. Shortwave infrared penetrated thin vegetation, detecting soil moisture variations that indicated buried structures. The machine learning revolution transformed site discovery. Dr. Dylan Davis from Pennsylvania State University developed neural network algorithms trained on thousands of known archaeological sites. The algorithm learned to recognize patterns, specific combinations of topography, vegetation, soil characteristics, and landscape context that indicated human modification. When applied to satellite imagery of unsurveyed regions, the algorithm automatically flagged locations with high probability of archaeological significance. The success rate was remarkable. In a test covering 5,000 square kilometers of the Bolivian Amazon, the algorithm identified 143 potential sites. Ground verification teams investigated 89 of these locations and confirmed 73 as genuine archaeological sites, an 82% success rate. The algorithm was finding sites that human analysts examining the same imagery had missed. The pace of discovery accelerated dramatically. In 2020, approximately 26 Casarabe sites were known. By 2024, the number exceeded 180. Each new discovery refined understanding of settlement patterns, population distributions, and cultural practices. The technology was revealing the Amazon's hidden past faster than archaeologists could excavate and analyze the sites. The climate change connection. The Casarabe civilization's relationship with their environment offers sobering lessons for modern society. Paleoclimate studies show that despite the drought cycles that challenged their civilization, the overall climate of the Amazon during the Casarabe period was relatively stable compared to more recent centuries. Yet even within this stable period, relatively modest climate variations appear to have had significant social impacts. Modern climate change is producing shifts in Amazonian rainfall patterns far more dramatic than anything the Casarabe experienced. Annual rainfall in some parts of the Amazon has decreased by over 20% since 1980, and climate models project further declines. The archaeological record shows that sophisticated civilizations managing complex ecosystems can be vulnerable to environmental changes, a lesson that resonates as modern societies face their own climate challenges. The paleoclimate record showed that the Casarabe period, 500 to 1400 AD, fell within the medieval climate anomaly, a period of relatively warm and stable conditions globally. In the Amazon, lake sediment cores indicated that baseline rainfall during this period was similar to 20th century averages, with variability of approximately 1–525% around the mean. The drought episodes that stressed Casarabe civilization represented deviations of 30–40% from baseline significant, but not unprecedented. Modern climate change was producing more extreme shifts. Rainfall monitoring stations across the Amazon showed declining trends since 1980. The southern Amazon, including the Casarabe region, experienced the most severe declines, with annual rainfall decreasing by 20–25% compared to mid-20th century levels. Climate models projected that under high-emission scenarios, rainfall could decline an additional 20–30% by 2100, reaching levels unprecedented in the paleoclimate record. The comparison highlighted the Casarabe vulnerability. Their sophisticated water management systems were optimized for specific rainfall regimes. When drought struck, the systems could buffer short-term variability but ultimately failed under sustained stress. Modern agricultural systems faced similar vulnerabilities. Infrastructure and practices optimized for historical climate conditions might fail as conditions shifted beyond design parameters. The lesson extended beyond simple climate determinism. The Casarabe hadn't collapsed simply because of drought. They had persisted through multiple severe drought episodes, adapting through engineering innovations. The final collapse occurred during a return to normal rainfall, suggesting that failure resulted from complex interactions between environmental, social, and economic factors rather than climate alone. This nuanced relationship between climate and society offered insights for modern challenges. Climate change wouldn't simply cause societal problems, rather, it would stress existing systems, potentially triggering cascading failures in food production, infrastructure, economic networks, and social institutions. Resilience required not just engineering solutions, but also social flexibility, economic diversification, and institutional capacity to coordinate responses. The archaeological record also showed that collapse wasn't inevitable. Casarabe civilization survived and even flourished during drought periods, suggesting that with appropriate adaptations, societies could persist through significant environmental stress. The challenge lay in implementing adaptations quickly enough and comprehensively enough to address accelerating change. The ongoing excavations. Archaeological work at Casarabe sites continues, with new discoveries emerging each field season. In 2024, excavations at a site called Loma Capitan uncovered what appeared to be a workshop area containing thousands of stone tools in various stages of manufacture. The discovery provided unprecedented insights into ancient craft production, showing not just finished products but the entire manufacturing process. Nearby, excavators found evidence of a structure that may have served as a school or training center where apprentices learned stoneworking techniques. In another area, geophysical surveys identified what appeared to be a previously unknown platform mound buried under centuries of soil accumulation. The site had been occupied for centuries after the main Kasarabe collapse, suggesting some populations maintained the traditions and technologies of their predecessors longer than previously thought. The Loma Capitan excavations were led by Dr. Carla Jaimez Betancourt from the University of Bonn. The workshop area covered approximately 200 square meters on a low terrace overlooking a stream. The excavation revealed a dense concentration of lithic debitage waste flakes produced during stone tool manufacture, with over 15,000 pieces recovered from a 10 square meter unit. The assemblage showed the complete reduction sequence. Large nodules of raw material appeared, some showing initial flake removals. Partially worked cores in various stages represented sequential steps in the manufacturing process. Broken or misstruck pieces showed the errors and accidents inevitable in stoneworking. Finished tools included axes, chisels, scrapers, and cutting implements. The complete sequence from raw material to finished product revealed technological choices and skill levels. Most significantly, the spatial distribution suggested organized production. One area contained primarily early-stage reduction, large flakes and roughly shaped cores. Another area showed evidence of detailed shaping and finishing work. A third area appeared to be a discard zone, where broken and exhausted cores were disposed of. This spatial organization suggested multiple craftspeople working simultaneously, perhaps specializing in different stages of production. The possible training structure was a rectangular building identified by post holes, forming a 12 by 8 meter outline. Inside, excavators found several teaching sets, collections of stones showing progressive stages of tool manufacture, arranged in sequence from raw nodule through finished tool. These appeared to be demonstrations, physical examples showing learners how tools should be produced. Modern stoneworking instructors use similar teaching methods, suggesting ancient master craftspeople also employed systematic pedagogical approaches. The buried platform mound represented an unexpected discovery. Ground-penetrating radar, conducted as part of routine site survey, detected a subsurface anomaly, an area of higher density material showing geometric form. Test excavations revealed a platform mound that had been buried under approximately 1.5 meters of soil, accumulated through natural processes over centuries. Radiocarbon dates from the mound's construction showed it was built around 1350 AD, late in the Kasarabe sequence. But dates from occupation, debris on and around the mound extended to 1480 AD, 80 years after the conventional end of Kasarabe civilization. The late dates indicated that some communities continued occupying and maintaining Kasarabe-style settlements long after the major urban centers collapsed. This suggested the collapse was gradual and uneven, with different communities experiencing different trajectories. The heritage question. Modern indigenous communities in the Llanos de Moxos region have complex relationships with the archaeological sites in their territories. Some groups maintain oral traditions describing ancient cities and great ancestors who built the mounds, though these traditions have been filtered through centuries of cultural change and the traumatic disruptions of colonialism. Genetic studies confirm that modern indigenous populations are descendants of the Kasarabe people. But cultural continuity is harder to trace. In recent years, archaeological projects have increasingly involved local communities in research, design, and interpretation. Recognizing that indigenous knowledge systems offer valuable perspectives on the past, some communities have begun incorporating archaeological findings into their own historical narratives, reclaiming a past that colonialism attempted to erase. The Bao people, whose language and territory overlap with the ancient Kasarabe region, maintain oral histories that speak of ancient times when the Old Ones built the hills. These traditions describe powerful leaders who commanded workers to pile earth, creating the platform mounds that dot the landscape. Some stories mention catastrophes, floods, droughts, or conflicts that forced abandonment of the ancient cities. While these narratives have clearly evolved over centuries of retelling, they preserve memories of the archaeological past. Genetic studies showed direct continuity. DNA analysis of Baure, Pornaka, and other local indigenous groups revealed they carried genetic markers characteristic of ancient Kasarabe populations. They were literal descendants of the civilization that built the earthworks, though the cultural traditions connecting them to that past had been disrupted by centuries of colonial oppression, forced relocations, and cultural suppression. Archaeological projects increasingly practiced community-based research. Rather than simply informing communities that excavations would occur, archaeologists involved community members in deciding research priorities, designing projects, and interpreting findings. Indigenous fieldworkers participated in excavations, learning archaeological methods, while contributing traditional ecological knowledge that helped interpret ancient practices. The Museo Kenneth Lee, in Trinidad, Bolivia, developed exhibits presenting Kasarabe civilization with input from indigenous consultants. Rather than describing the ancient people as mysterious vanished cultures, the exhibits emphasized continuity. These were the ancestors of living people, their technologies and knowledge preserved in modified forms in contemporary indigenous practices. Some communities used archaeological findings to support land rights claims, demonstrating that their ancestors had built and managed the landscape for centuries, provided historical basis for territorial claims against encroachment by ranchers and agricultural developers. The earthworks became not just archaeological sites but political resources in contemporary struggles over land and resources. Tensions sometimes arose. Some communities felt archaeologists extracted knowledge from their territories without adequate compensation or recognition. Others questioned whether disturbing burial sites and sacred places was appropriate even for scientific purposes. The archaeological community increasingly recognized these concerns, developing protocols for respectful research that balanced scientific goals with community values. The unexcavated sites. Despite decades of research, the vast majority of Kasarabe sites remain unexcavated. LiDAR surveys have identified hundreds of locations showing archaeological potential, but limited funding and the logistical challenges of working in remote rainforest locations mean that comprehensive excavation of even a single major site can take years or decades. Many of the most promising sites are located in areas that are difficult to access, requiring days of travel by boat and on foot to reach. Some sites lie in territories affected by coca production and drug trafficking, making archaeological work impossible for security reasons. Other sites are threatened by deforestation and agricultural expansion, with new LiDAR data sometimes revealing sites that no longer exist on the ground, destroyed by land clearing before archaeologists could document them. The race to study these sites before they disappear has become increasingly urgent. The scale of unexcavated sites was sobering. Of the approximately 180 known Kasarabe sites, fewer than 30 had received systematic excavation beyond test trenches. The two major urban centres, Kotoka and Landivar, had been subject to multiple research projects, but remained largely unexplored. Less than 2% of their areas had been excavated. The secondary sites were even less studied, with most known only from surface surveys and remote sensing data. Funding limitations constrained research. A typical field season conducting excavations at a Kasarabe site required $80,000 to $150,000, covering equipment, supplies, worker salaries, transportation, laboratory analysis, and radiocarbon dating. With limited archaeological funding available globally, and even more limited resources directed to South American archaeology, comprehensive programs at multiple sites were financially impossible. The logistical challenges were equally daunting. Reaching remote sites required weeks of preparation, coordinating boats, vehicles, pack animals, and porters. During rainy season, many sites became inaccessible as roads turned to mud and streams flooded. During dry season, water scarcity made maintaining field camps difficult. Equipment had to be carried in, excavation backdirt had to be screened, artifacts required careful curation in humid conditions without electricity or climate control. Security issues affected some regions. Areas of coca cultivation saw occasional violence between growers, traffickers, and authorities. Archaeological teams risked being caught in confrontations or mistaken for law enforcement. Some promising sites identified in LiDAR surveys lay in zones where research was simply too dangerous. The threat of destruction added urgency. Satellite imagery showed deforestation advancing across the region at rates of 1 to 2% annually. Archaeological sites that had survived centuries under forest cover disappeared within hours once clearing began. LiDAR data from 2018 showed 12 significant sites in a particular area. By 2023, ground verification found that 5 had been destroyed by agricultural conversion. The earthworks were bulldozed, the artifacts scattered, the scientific information lost forever. Conservation efforts attempted to address the threat. Working with Bolivian authorities, archaeologists succeeded in establishing protected zones around some major sites. But protection required resources, guards, fencing, monitoring that were rarely available. Many sites remained vulnerable, their destruction only a matter of time unless urgent action preserved them. The Amazon's hidden history, the discoveries at Casarabe sites and across the Amazon, have fundamentally changed our understanding of pre-Columbian America. The image of the Amazon as a pristine wilderness, only sparsely inhabited by small bands of hunter-gatherers, has been replaced by a recognition that the rainforest was home to complex societies numbering in the millions. These civilizations engineered their landscapes on a massive scale, building cities connected by roads and canals, managing forests, and engaging in trade networks spanning thousands of kilometers. They developed their own solutions to the challenges of living in the tropical environment. Solutions that didn't rely on old-world technologies, but were no less sophisticated for being different. The Amazon's past was far more complex, populated, and culturally rich than anyone imagined just a generation ago. And with each new discovery, more of this hidden history emerges from beneath the jungle canopy. The transformation in understanding occurred remarkably quickly. In 1990, most archaeologists believed the Amazon couldn't support large populations. The poor soils, dense vegetation, and difficult environment seemed to preclude anything beyond small mobile groups. Major civilizations developed in the Andes highlands or Mesoamerican valleys, places with better conditions for agriculture and construction. The Amazon was peripheral, sparsely populated, culturally simple. By 2025, this view had been completely overturned. LiDAR surveys revealed hundreds of significant sites, urban centers, engineered landscapes, earthworks of extraordinary scale. Paleoenvironmental studies showed that pre-Columbian populations had modified enormous areas, creating anthropogenic forests and enriched soils. Genetic studies indicated populations in the millions before European contact. The Amazon had been a center of innovation and cultural complexity, not a marginal backwater. The implications extended beyond archaeology. Ecologists recognized that pristine rainforest was actually a recovering cultural landscape. Conservation strategies shifted to incorporate understanding of historical human management. Indigenous land rights movements found historical validation in archaeological evidence of their ancestors' sophisticated societies. Political debates over Amazon development gained new dimensions as the region's human past became visible. The technological revolution in archaeological methods meant discoveries would continue accelerating. Each advance in analytical techniques extracted more information from existing collections. Machine learning algorithms would identify sites faster than humans could investigate them. The hidden history was becoming visible at an ever-increasing pace, but fundamental questions remained unanswered. Why did these civilizations collapse? What were their political organizations? How did their religious beliefs shape their engineering? What languages did they speak? How did they educate their children, resolve disputes, celebrate important events? The answers lay buried beneath the jungle, waiting in the sites yet to be excavated, the artifacts yet to be analyzed, the patterns yet to be recognized. The Amazon held secrets that would take generations to uncover fully. Each excavation revealed not just answers, but new questions. Each discovery showed how much remained unknown. The jungle canopy that had concealed this past for centuries was finally being penetrated, revealing glimpses of civilizations that rivaled any in the ancient world. The Amazon's hidden history was being written, one discovery at a time, bringing into focus a past that had never truly disappeared, only waited patiently to be rediscovered. The LiDAR revolution that changed everything. In 2002, a small aircraft equipped with experimental laser scanning equipment flew systematic passes over the Bolivian Amazon. The technology, called LiDAR light detection and ranging, worked by firing millions of laser pulses per second toward the ground below. Most pulses bounced off the jungle canopy, but a small percentage penetrated through gaps in the foliage, striking the forest floor and returning precise elevation data. When researchers at the University of Pennsylvania processed this data months later, they discovered something that made them question their equipment's calibration. Beneath the unbroken green, the scans revealed massive geometric earthworks, perfectly straight lines, precise circles, and rectangular platforms arranged in patterns that could only be artificial. The research team spent 3 weeks verifying their results. They recalibrated the equipment twice. They processed the raw data using different algorithms. Every analysis produced the same impossible conclusion: there were cities under the jungle. Dr. Clark Erickson, the project's lead archaeologist, later described his first reaction as disbelief. The patterns were too regular, too extensive, too geometrically precise to be natural formations, yet they were there, invisible to anyone standing on the forest floor, revealed only through technology that could strip away the vegetation digitally. The LiDAR system they used was primitive by today's standards. It captured approximately 10,000 pulses per square meter. Modern systems capture over 100,000. The resolution was coarse, the processing time measured in months rather than hours, but it was enough. The data showed earthworks extending across hundreds of square kilometers, organized in patterns that suggested urban planning on a scale that no one had imagined possible for pre-Columbian Amazonia. What made the discovery particularly significant was its location. The Llanos de Moxos had been surveyed multiple times by ground-based archaeological teams. Researchers had walked through these areas, had dug test pits, had interviewed local residents, yet they had seen nothing. The forest concealed everything. Tree roots broke apart ancient structures. Vegetation filled in depressions and covered mounds. Centuries of leaf fall created a layer of organic matter that buried features under meters of soil. Only by looking from above, using laser pulses that could penetrate the canopy, could the true landscape be revealed. The implications extended beyond a single site. If major settlements could remain hidden under the Amazon rainforest, then archaeological surveys that relied on ground visibility had missed vast amounts of evidence. Traditional estimates of pre-Columbian Amazonian populations, based on the assumption that archaeologists had identified most major sites, suddenly seemed inadequate. The technology revealed that the forest was hiding secrets, and raised the question of how many other undiscovered cities lay beneath the green canopy. By 2024, LiDAR surveys had been conducted across approximately 5% of the Amazon basin. Each new survey revealed more sites. The pattern was consistent. Wherever archaeologists looked with sufficient technology, they found evidence of ancient occupation. The jungle had preserved these sites while simultaneously concealing them, creating an archive of human history that was only now being read. The Kasarabe culture, cities in the wilderness. The earthworks belong to the Kasarabe culture, a civilization that flourished between 500 and 1400 AD in what is now the Llanos de Moxos region of Bolivia. For decades, anthropologists had dismissed this area as too hostile for large-scale settlement. The seasonal flooding, dense vegetation, and isolation seemed to preclude anything beyond scattered villages. But the LiDAR data told a different story. The scans revealed at least 26 distinct settlement sites spread across 4,500 square kilometers. 2 of these sites, Kotoka and Landivar, showed characteristics of urban centers. Each covered more than 100 hectares and featured massive platform mounds rising over 20 meters high, connected by raised causeways that stretched for kilometers through the floodplain. The discovery challenged fundamental assumptions about environmental limitations on cultural development. The Llanos de Moxos floods annually, with water levels rising up to 5 meters during the wet season, inundating approximately 70% of the landscape. Modern settlements in the region consist of small villages built on natural high ground, with populations that fluctuate seasonally as residents move to avoid flooding. The idea that this environment could support cities housing thousands of people seemed implausible, yet the archaeological evidence was undeniable. The urban centres weren't built despite the flooding, they were engineered specifically to exploit it. The platform mounds served as elevated foundations that remained above water even during peak flood periods. The causeways connected different sections of the settlements, creating transportation networks that functioned year-round. The entire landscape had been modified to turn seasonal inundation from a liability into an asset. Kotoka, the larger of the two urban centres, covered 147 hectares, roughly equivalent to 200 football fields. The central platform mound rose 22 metres above the surrounding plain, visible from kilometres away across the flat landscape. Surrounding this central feature were at least 19 smaller mounds, arranged in a roughly circular pattern, connected by raised pathways. The precision of the layout suggested deliberate planning rather than organic growth over time. Landivar, located 28 kilometres northeast of Kotoka, followed a similar design but on a slightly smaller scale. Its central mound measured 18 metres in height and was surrounded by 15 secondary platforms. What made Landivar particularly interesting was a massive rectangular reservoir adjacent to the settlement, measuring 800 metres by 400 metres and capable of storing millions of litres of water. The reservoir's walls showed evidence of careful engineering, with sloped sides and drainage channels that controlled water levels. The relationship between Kotoka and Landivar raised intriguing questions. Were they rival cities competing for resources and political control? Or were they complementary centres in a unified political system, perhaps serving different administrative or ceremonial functions? The causeways connecting the two sites suggested coordination rather than competition. But without written records, the political organisation of Kasarabe civilization remained a matter of interpretation, with each new archaeological discovery adding pieces to an incomplete puzzle. What was clear was that the Kasarabe people had created something unprecedented in the Amazon true urban centres, with populations numbering in the thousands, supported by sophisticated engineering and organised through some form of centralised authority, capable of mobilising labour for massive construction projects. Engineering the impossible. Water management systems. What puzzled researchers most wasn't just the scale of these settlements, but the sophisticated infrastructure that supported them. Ground-penetrating radar surveys revealed an extensive network of canals, reservoirs, and water control structures engineered to manage the seasonal floods that inundate the region every year. Some reservoirs measured over 2 kilometers in length and appeared to be connected by channels that followed precise geometric alignments. The system suggested knowledge of hydraulic engineering that allowed the Kasarabe people to turn the region's greatest liability and its flooding into an agricultural advantage. Chemical analysis of soil samples from ancient field systems showed elevated levels of nutrients, indicating intensive cultivation using techniques that enriched rather than depleted the land. The engineering principles underlying these water management systems became clearer as researchers conducted detailed topographic surveys using differential GPS equipment accurate to within 2 centimeters. The surveys revealed that the canals weren't simply dug at random but followed carefully calculated gradients that ensured water flow without causing erosion. The typical gradient was approximately 0.1%, a drop of just 10 centimeters over 100 meters, shallow enough to prevent scouring but sufficient to keep water moving. The reservoir systems showed even more sophistication. Many featured multiple chambers connected by controlled spillways that allowed water to be directed to different areas depending on seasonal needs. During the dry season, these reservoirs provided water for crops and human consumption. During floods, they served as storage areas that captured excess water, preventing it from inundating agricultural fields. The spillway designs incorporated elements that modern engineers recognized as effective: broad overflow sections that distributed flow evenly, energy dissipation features that prevented downstream erosion, and what appeared to be settling basins where silt could accumulate without clogging the system. Archaeological excavations of the canal systems revealed construction techniques that demonstrated sophisticated engineering knowledge. The canals weren't simply trenches cut into the earth. Their bottoms were lined with clay that had been carefully selected for its low permeability. Laboratory analysis showed the clay had plasticity indices optimized for water retention. The sides of the canals were reinforced with layers of gravel that prevented collapse. In some sections, excavators found evidence of wooden revetments, posts and planks used to stabilize canal banks in areas where soil conditions were particularly unstable. The scale of the water management infrastructure was staggering. Aerial surveys using drones mapped over 200 kilometers of canals in the Kasarabe heartland alone. Some of these canals were clearly designed for transportation, with dimensions suitable for canoes, approximately 3 meters wide and 1.5 meters deep. Others were narrower and appeared to serve irrigation functions, carrying water from reservoirs to agricultural fields. The network was interconnected, with multiple redundant pathways that would have allowed the system to continue functioning even if individual segments became blocked or damaged. Perhaps most remarkably, the system included what appeared to be fish farming facilities. Several reservoirs showed evidence of internal partitions that created separate pools. Analysis of sediment from these pools revealed high concentrations of fish scales and bones, suggesting they had been used to raise fish in controlled conditions. This represented not just water management, but aquaculture. The deliberate cultivation of aquatic species, a technology that provided protein for urban populations. The pyramid builders of the Amazon. The platform mounds discovered at Kasarabe sites bore an uncanny resemblance to stepped pyramids found in Mesoamerica. Yet they appeared to have developed independently. Excavations at one site called Loma Salvatierra revealed a construction technique that defied expectations. Rather than simply piling earth, the builders had created these structures using layers of different materials, clay, gravel, and organic matter, arranged in precise sequences that provided both stability and drainage. Radiocarbon dating of organic materials found between layers established construction timelines spanning several centuries, with each generation apparently adding to the structures. The largest platforms required moving an estimated 500,000 cubic meters of earth, a feat that would have demanded the coordinated labor of thousands of workers. The excavation at Loma Salvatierra proceeded slowly, with archaeologists removing soil in 5-centimeter increments while documenting every layer. What emerged was a construction history that revealed planning and engineering that rivaled contemporary civilizations on other continents. The platform's foundation, at the very bottom of the excavation 8 meters below the summit, consisted of a base layer of coarse gravel, approximately 30 centimeters thick. This layer served as drainage, preventing water from accumulating at the base and destabilizing the structure. Above the gravel, the builders had placed alternating layers of clay and sandy soil, each layer between 10 and 20 centimeters thick. The layering wasn't arbitrary. Laboratory analysis showed that the clay layers had high plasticity and low permeability, while the sandy layers were more permeable. This alternating pattern created a structure that was stable during both dry and wet seasons. During rains, water could percolate through the permeable layers, while the clay layers prevented rapid saturation that might cause collapse. Interspersed with these soil layers were organic layers, compacted vegetation, charcoal, and what appeared to be deliberately deposited refuse, including broken pottery and food remains. Initially, excavators assumed these organic layers were simply construction debris, but radiocarbon dating revealed they served another purpose. By dating the organic material in different layers, archaeologists could establish a construction chronology. The results showed that Loma Salvatierra was built in at least 7 distinct phases, spanning approximately 400 years, from roughly 800 AD to 1200 AD. Each construction phase had added between 1 and 2 meters to the platform's height. This suggested that rather than being built as a single massive project, these platforms were constructed incrementally, with each generation adding to the work of their predecessors. The cultural continuity required to maintain such projects across centuries spoke to stable social institutions and persistent religious or political motivations that transcended individual lifetimes. The summit of Loma Salvatierra revealed the final phase of construction. A flattened area, approximately 40 meters by 30 meters, with evidence of substantial structures. Post holes measuring 30 centimeters in diameter were arranged in rectangular patterns, indicating buildings with walls and roofs. The density of artifacts found on the summit's ceramic vessels, stone tools, and decorative objects suggested intensive use, possibly as an elite residence or ceremonial center. The engineering achievement was even more impressive when considered in context. Moving 500,000 cubic meters of earth meant that workers had excavated, transported, and carefully placed approximately 800,000 tons of material. If a worker could move 1 cubic meter of earth per day, a reasonable estimate for hand labor, Using baskets and simple tools, the project would have required 500,000 person-days of labor. Spread across the 400-year construction period, this amounted to continuous work by approximately 3 to 4 people every single day. But construction likely occurred in intensive bursts rather than continuous low-level effort, suggesting periodic mobilizations of much larger labor forces. Artifacts that shouldn't exist. In 2019, excavations at one of the Kasarabe urban centers uncovered a cache of ceramic vessels buried beneath what appeared to be a ceremonial plaza. The vessels themselves were unremarkable, typical of the region and period. But their contents changed the conversation. Inside, archaeologists found metal objects, including copper axes, decorative pieces, and what appeared to be bronze alloy items. The presence of bronze was particularly significant. Traditional archaeological models held that metallurgy in the Amazon remained limited to simple copper working. These artifacts suggested the Kasarabe people had mastered alloy creation, mixing copper with tin in ratios that required both technical knowledge and access to tin sources located hundreds of kilometers away in the Andes highlands. The cache contained 23 metal objects in total. 15 were copper axes, with blade widths ranging from 8 to 12 centimeters, showing signs of use nicks in the cutting edges and polish from handling. 5 were decorative items, including what appeared to be status symbols or ritual objects. A crescent-shaped pendant, 2 circular ornaments with intricate geometric designs, and 2 items whose function remained unclear. But it was the 3 remaining objects that generated the most excitement and controversy. These 3 pieces were analyzed using X-ray fluorescent spectroscopy, a non-destructive technique that identifies elemental composition. The results showed that they contained not just copper, but significant amounts of tin, between 8% and 12% tin by weight. This composition defined them as bronze, an alloy that required intentional creation rather than occurring naturally. The technology for bronze production, long thought to be absent from Amazonia during this period, was apparently present in Kasarabe culture. The implications cascaded through multiple dimensions of archaeological interpretation. First, the presence of tin meant the Kasarabe people had access to tin sources. The nearest known tin deposits were in the Bolivian highlands, over 300 kilometers away across difficult terrain. This suggested either long-distance trade networks or territorial control, extending far beyond the immediate Llanos de Moxos region. Either scenario required social organization and economic infrastructure more complex than previously attributed to Amazonian cultures. Second, bronze production required sophisticated metallurgical knowledge. Creating bronze isn't simply a matter of mixing copper and tin. The metals must be heated to temperatures exceeding 1000 degrees Celsius, combined in specific ratios, and processed using techniques that prevent oxidation and other defects. The skill required suggested specialized craftspeople who had mastered these techniques through years of training and experimentation. Third, the cache's context, buried beneath a ceremonial plaza, suggested these weren't everyday tools but valuable items with special significance. The deliberate burial implied ritual deposition, possibly an offering to sanctify the plaza or mark an important event. The inclusion of both used tools and decorative items suggested the cache represented a collection of valuable objects rather than manufacturing waste or discarded goods. Subsequent analysis using lead isotope techniques attempted to trace the origin of the copper and tin in the bronze objects. Lead isotopes vary depending on geological source, creating a unique fingerprint for metal from different mining regions. The results matched copper sources in the Lake Titicaca Basin and tin deposits near Oruro, both in the Bolivian highlands. This confirmed that raw materials were being transported from the Andes to the Amazon, a journey that would have required organized trade or tribute systems. The discovery raised a fundamental question. What else didn't archaeologists know about Kasarabe technology? If bronze working was present when models said it shouldn't be, what other supposedly absent technologies might await discovery? Each artifact challenged assumptions and opened new questions about the sophistication of ancient Amazonian civilizations. The mystery of the geoglyphs. West of the Kasarabe heartland, in the Brazilian state of Acre, deforestation in the 1,980 seconds began revealing even more perplexing features. As cattle ranchers cleared jungle for pasture, They exposed enormous geometric earthworks, circles, squares, and complex patterns carved into the Earth centuries ago. By 2024, over 450 of these geoglyphs had been documented, covering an area of approximately 13,000 square kilometers. The shapes were massive. Some circular geoglyphs measured 300 meters in diameter, with ditches up to 11 meters wide and 4 meters deep. The precision of the geometry baffled researchers. Many shapes were perfectly circular or square, within a margin of error that suggested sophisticated surveying techniques. But perhaps most mysteriously, excavations found little evidence of permanent settlement within these structures. The first systematic study of the Acre geoglyphs began in 2008, when archaeologist Also Ranzi from the Federal University of Acre organized aerial surveys using small planes equipped with GPS-enabled cameras. The surveys revealed patterns that were invisible from ground level. From the air, the shapes emerged clearly perfect: circles, precise squares, and compound designs combining multiple geometric forms. Some sites featured concentric circles, like enormous targets carved into the red earth. Others showed squares within circles, or hexagonal patterns with connecting pathways. What made these geoglyphs particularly enigmatic was their apparent purpose or lack thereof. Unlike the Kasarabe platform mounds, which clearly served as foundations for buildings and ceremonial structures, excavations within the enclosed areas found minimal pottery, few tools, and almost no food remains. The ditches themselves had been carefully excavated, with vertical walls and flat bottoms, suggesting they weren't defensive structures hastily dug during emergencies, but rather carefully planned constructions built over extended periods. Radiocarbon dating of charcoal and organic materials from the ditch fill provided dates ranging from 200 BC to 1283 AD, indicating these structures were built and used over a period of roughly 1,500 years. This meant the geoglyphs predated the Kasarabe urban centers and continued to be constructed and maintained throughout the period of Kasarabe florescence. The cultural continuity implied by such long-term construction suggested these structures held enduring importance to Amazonian peoples. Several theories attempted to explain the geoglyphs' function. Some researchers proposed they served astronomical purposes, with the geometric patterns aligned to celestial events. Statistical analysis of the orientations of 81 geoglyphs found that 37% showed alignments within 5 degrees of cardinal directions, and several aligned with solstice, sunrise, or sunset positions. While this suggested some astronomical awareness, the percentage wasn't high enough to prove celestial observation was the primary purpose. Another theory suggested the geoglyphs served as ceremonial gathering spaces. The enclosed areas could have accommodated hundreds of people, and the geometric precision might have held symbolic or religious significance. Ethnographic parallels with modern indigenous Amazonian groups, many of whom organize their villages in circular patterns and attribute cosmological meaning to geometric forms, lent some support to this interpretation. A third hypothesis proposed the geoglyphs were territorial markers, visual declarations of land ownership or resource control visible from elevated positions in the landscape. The distribution pattern, with geoglyphs spaced at relatively regular intervals, suggested they might have divided the landscape into distinct zones, each associated with different groups or families. Yet none of these theories fully explained the archaeological evidence. The geoglyphs remained enigmatic, massive construction projects that required thousands of hours of labor to create, but left almost no trace of the people who built them. The earth itself preserved the shapes while erasing the builders, creating monuments without context, geometry without obvious purpose. Reading the forest, terra preta, and ancient populations. Soil scientists working in the Amazon had long known about terra preta black earth patches of unusually fertile soil scattered throughout the rainforest. Chemical analysis showed these soils contained high concentrations of charcoal, bone, and pottery fragments, clearly indicating human origin. But recent studies using satellite imagery and machine learning algorithms to identify terra preta sites based on vegetation patterns suggested the extent of these anthropogenic soils was far greater than previously recognized. Some estimates now suggest that up to 10% of the Amazon basin, an area roughly the size of France, shows signs of ancient human modification. If these soils indicate settlements, the population of pre-Columbian Amazonia may have numbered in the millions, orders of magnitude higher than traditional estimates. The distinctive characteristics of Terra Preta made it identifiable even centuries after its creation. The soil was darker than surrounding Amazonian soils, almost black rather than the typical red or yellow. It contained 2 to 3 times more organic carbon, and its pH was typically between 5.5 and 6.5, significantly less acidic than unmodified Amazonian soils that often measured pH 4 or lower. Perhaps most remarkably, Terra Preta soils remained fertile even after centuries of abandonment, while natural Amazonian soils quickly became depleted when cleared and cultivated. Laboratory analysis revealed the secret of this persistent fertility. The soil contained high concentrations of biochar charcoal, created through low-temperature burning of organic matter. Unlike ash from high-temperature fires, biochar is extremely stable, persisting in soil for centuries without decomposing. Its porous structure provides habitat for beneficial soil microorganisms and increases the soil's ability to retain nutrients and water. Chemical tests showed Terra Preta contained 3 to 8 times more phosphorus, calcium, and nitrogen than surrounding soils, the key nutrients required for plant growth. But Terra Preta wasn't simply the accidental result of cooking fires and refused disposal. The composition suggested intentional soil management. Archaeological excavations revealed that Terra Preta deposits were often layered, with distinct horizons showing different compositions. Some layers contained high concentrations of fish bones and turtle shells, others showed elevated ceramic content, and still others consisted primarily of charcoal. This layering indicated deliberate addition of different materials, suggesting ancient Amazonians understood soil fertility and actively worked to maintain productive land. The distribution of Terra Preta sites across the Amazon provided indirect evidence of population density. Mapping projects identified over 3,000 distinct Terra Preta sites in the Brazilian Amazon alone, with individual sites ranging from less than 1 hectare to over 300 hectares. If each hectare of Terra Preta represented approximately 10 to 20 people, a conservative estimate based on ethnographic comparisons, then the documented sites alone represented populations in the hundreds of thousands, and surveys had covered less than 5% of the Amazon basin, suggesting the true number of sites could be an order of magnitude higher. Recent research using machine learning algorithms trained on multispectral satellite imagery has accelerated the discovery of Terra Preta sites. The algorithms detect subtle differences in vegetation that correlate with anthropogenic soils. Certain plant species grow preferentially in Terra Preta, creating spectral signatures visible from space. In 2023, automated analysis of satellite imagery covering 50,000 square kilometers of previously unsurveyed Amazon identified 847 potential Terra Preta sites. Ground verification confirmed that 82% were authentic, demonstrating that satellite-based discovery could revolutionize understanding of ancient Amazonian settlement patterns. The implications extended beyond simple population estimates. If millions of people had inhabited the Amazon before European contact, then the pristine rainforest encountered by European explorers in the 16th century was actually a recovering landscape, a forest growing back over lands that had been managed and cultivated for millennia. The Amazon wasn't wilderness, but rather a cultural landscape, shaped by human hands across centuries before disease and conquest depopulated the region. The Lost Gardens, Domestication in the Jungle, ethnobotanical surveys conducted between 2010 and 2020 revealed another surprise hidden in plain sight. Researchers cataloguing tree species in supposedly pristine rainforest areas noticed unusual patterns in species distribution. Certain valuable trees, Brazil nuts, cacao, and various palms appeared in concentrations that defied random dispersal. Statistical analysis showed that these trees were significantly more common near archaeological sites and along ancient causeways identified through LiDAR. The implication was startling. Large portions of the Amazon rainforest were not pristine wilderness, but rather ancient forest gardens, deliberately shaped by indigenous peoples who had cultivated useful species across the landscape. This suggested a level of environmental management that persisted in the forest composition even centuries after the cultures that created these patterns had collapsed. The research began with systematic botanical transects, straight-line surveys through forest areas, recording every tree larger than 10 centimeters in diameter. Researchers documented species, measured trunk circumference, and recorded GPS coordinates for each tree. When this data was analyzed using Geographic Information Systems software, patterns emerged. Brazil nut trees, which produce nutritious seeds that have been a staple food source for Amazonian peoples for millennia, appeared in clusters rather than random distributions. Near identified archaeological sites, Brazil nut trees occurred at densities 5 to 10 times higher than in areas distant from human occupation. Similar patterns appeared for dozens of other useful species. Cacao trees, the source of chocolate, showed 7 times higher density near archaeological sites. Various palm species used for construction, food, and fiber appeared in elevated concentrations along ancient pathways and near settlement areas. Even the spatial arrangement showed patterns. Useful trees were often planted in groves or linear arrangements that suggested deliberate cultivation rather than natural dispersal. Genetic analysis of these tree populations provided additional evidence of human management. Researchers collected leaf samples from Brazil nut trees across several study areas and analyzed their DNA. The genetic diversity within clusters near archaeological sites was lower than in more distant areas, suggesting these populations had been established from a limited number of parent trees, exactly what would be expected if people had planted seeds gathered from preferred trees, rather than allowing natural reproduction. The genetic patterns indicated that ancient Amazonians had practiced selection, choosing trees with desirable characteristics and propagating them across the landscape. The timescale of this forest engineering was staggering. Brazil nut trees can live for 500 years or more. Many of the trees documented in these surveys had germinated in the 1500s or 1600s after European contact, but possibly planted from seeds gathered from cultivated trees planted centuries earlier. Some of the oldest trees, estimated at 600 to 800 years old through core sampling, would have been seedlings during the height of Cassarabe civilization. These trees were living connections to the pre-Columbian past, botanical artifacts that had outlived the civilizations that planted them. The concept of forest gardens challenged Western categories that separated wild from cultivated landscapes. Ancient Amazonians hadn't cleared the forest to create farms in the European sense. Instead, they had modified the existing forest, enriching it with useful species while maintaining the overall forest structure. This was agriculture, but agriculture that worked with rather than against the forest ecosystem. Computer modeling based on the documented distribution patterns suggested that at least 12% of the Amazon's mature forest shows species compositions influenced by ancient human management. In some areas near major archaeological sites, the percentage reached 30% or higher. If these estimates were accurate, then the Amazon rainforest, often held up as Earth's last great wilderness, was actually one of the world's largest and oldest anthropogenic landscapes, a garden that had been cultivated for over a millennium before being abandoned to grow wild again. The practice had practical implications for modern conservation and sustainable development. Terra preta soils and forest gardens demonstrated that human habitation didn't necessarily degrade the Amazon environment. Done correctly, human management could actually enhance forest productivity and biodiversity. Modern initiatives have begun incorporating these principles, teaching contemporary Amazonians techniques based on ancient practices, creating a living link between past and present. Expedition to the Uncontacted Zone. In March 2023, a joint Brazilian-American archaeological team received rare government permission to conduct a brief expedition into a region of the Amazon inhabited by uncontacted indigenous peoples. The expedition, strictly limited to flyovers and remote sensing, sought to investigate LiDAR anomalies detected in previous surveys. What the scans revealed was unprecedented evidence of active earthwork construction and maintenance in an area considered untouched by modern civilization. The geometric patterns were smaller than those at Cassarabe sites but showed similar design principles. Thermal imaging detected what appeared to be controlled burns being used to maintain cleared areas within the forest. The discovery suggested that some Amazonian groups were still practicing the landscape modification techniques of their ancestors, providing a living link to pre-Columbian engineering traditions. The region in question covered approximately 800 square kilometers in the western Brazilian Amazon. Along the border with Peru, Brazilian government policy strictly prohibited physical contact with the estimated 100 to 150 uncontacted people living in this area, protecting them from disease exposure and respecting their evident desire for isolation. But satellite imagery had detected forest clearings and what appeared to be earthworks, raising questions about whether these represented new construction or merely the remnants of past occupation. The expedition aircraft, a twin-engine plane equipped with high-resolution cameras, thermal imaging equipment, and LiDAR sensors, flew systematic passes at an altitude of 1,000 meters, high enough to be invisible from the ground but low enough to capture detailed data. The flights took place over 3 days in March, during a brief period of clear weather between rainstorms. What the sensors recorded would reshape understanding of cultural continuity in the Amazon. The LiDAR data revealed at least 7 distinct circular earthworks within the uncontacted zone, each measured between 60 and 120 meters in diameter, with surrounding ditches approximately 2 meters wide and 1 meter deep based on elevation differentials. The geometric precision was less refined than the ancient geoglyphs in Acre. These were rougher, with less perfect circles and irregular ditch depths. But the overall design principles were unmistakably similar. Someone was building geoglyphs in the 21st century, using techniques that hadn't changed in over 1,000 years. The thermal imaging revealed active human presence. Several heat signatures, consistent with fires, appeared within the earthwork enclosures, suggesting the structures were being actively used. Larger thermal anomalies indicated controlled burns, fires deliberately set to clear undergrowth while leaving larger trees standing. This technique, observed in other indigenous Amazonian groups, managed forest composition by removing invasive species and encouraging useful plants. The burns were small and controlled, affecting areas of 1 to 2 hectares. Nothing like the massive clearing fires associated with modern deforestation, but rather careful landscape management that had been practiced for generations. High-resolution photography captured details that hinted at construction methods. Along the edges of one circular earthwork, the cameras recorded what appeared to be freshly moved. Earth darker, soil exposed, where vegetation had been recently cleared. Photogrammetric analysis. Comparing images from this 2023 survey with satellite imagery from 2020 showed that this particular earthwork had expanded by approximately 15 meters in radius over the 3-year interval. Someone was actively enlarging the structure. The ethical implications of these observations sparked intense debate. Some archaeologists argued that documentary of living cultural practices, even from a distance, provided invaluable insights into how ancient earthworks were constructed and used. Others contended that any observation, even remote sensing, violated the uncontacted group's autonomy and potentially exposed them to risks if the information encouraged incursions into their territory. What remained undeniable was the finding itself: pre-Columbian landscape modification techniques had not disappeared. They were living practices, maintained across centuries of disruption, colonization, and cultural change. The uncontacted group, whoever they were, carried knowledge that stretched back to the age of the Kasarabe civilization and beyond. They were not remnants of a vanished past, but rather living practitioners of an unbroken tradition. Building earthworks in 2023, using techniques their ancestors had developed more than a millennium earlier. The acoustic mystery of the monuments. In 2021, acoustic engineers studying the platform mounds at several Kasarabe sites made an unexpected discovery. Using equipment designed to analyze sound propagation, they found that the structures possessed unusual acoustic properties. A person standing at the center of the largest platform mound could be heard clearly from distances exceeding 100 meters in all directions, far beyond what would normally be expected. Further analysis revealed that this wasn't accidental. The shape and dimensions of the platforms appeared to be optimized for sound amplification. Computer modeling showed that voices speaking from the platform tops would have been audible across much of the surrounding settlement. This suggested the platforms served as more than just ceremonial spaces. They were engineered communication devices, allowing leaders to address large populations before the invention of any form of sound amplification technology. The acoustic study was led by Dr. Miriam Kolar, an archaeoacoustician from Amherst College who had previously studied sound properties at ancient Andean sites, including Chavín de Huántar in Peru. Her team brought specialized equipment to measure sound reflection, diffusion, and propagation patterns at 3 different Kasarabe platform mounds. The testing protocol involved playing calibrated sound sources, both recorded human speech and pure tones at various frequencies, from different positions on and around the structures, while recording the sound at measurement points arranged in grids extending up to 200 meters from the platforms. The results revealed acoustic effects that exceeded natural expectations. A voice speaking at normal conversational volume measured at approximately 60 decibels at 1 meter from the source remained intelligible at distances up to 120 meters. Summit. In comparison, the same voice speaking from ground level became unintelligible beyond 30 to 40 meters. The platform was amplifying and projecting sound with an efficiency that approached purpose-built structures like Greek and Roman amphitheaters. Computer modeling of the acoustic properties revealed the mechanisms behind this amplification. The platform's shape, a raised, relatively flat summit with sloped sides, functioned similarly to a megaphone, directing sound outward and downward toward the surrounding area. The slope angle, typically between 30 and 40 degrees, appeared to be optimal for sound reflection. Steeper slopes would reflect sound upward, away from ground-level listeners. Shallower slopes would scatter sound diffusely. The observed angles directed sound precisely toward the area where an assembled audience would stand. The platform surfaces contributed additional acoustic effects. Unlike natural hillsides with irregular surfaces that scatter sound, the platforms had been carefully constructed with relatively smooth faces. Analysis of the construction layers showed that final surfacing often used fine clay that had been compacted and smoothed. This created a reflective surface that maintained sound coherence, rather than breaking up acoustic waves. The effect was subtle but significant. Speech intelligibility measurements showed a 15 to 20 decibel improvement on platforms with smooth surfaces compared to those where erosion had created irregular faces. Frequency analysis revealed another intriguing pattern. The platforms amplified certain frequency ranges more effectively than others. Specifically, frequencies between 500 and 2000 Hz, the range that carries most speech intelligibility information, were amplified preferentially. Lower frequencies, including the fundamental pitch of most human voices, were amplified less. This suggested that platform design had been optimized not just for volume but for clarity, enhancing the frequencies that allowed listeners to understand words rather than simply hear that someone was speaking. The team conducted a final experiment to test how these acoustic properties would have functioned during actual use. They gathered 50 volunteers who stood at various positions around one platform, while a speaker at the summit delivered a prepared text at normal speaking volume. Even at distances of 100 meters, listeners reported comprehension rates exceeding 80%. They could understand most of what was being said without any modern amplification. When the same experiment was repeated with the speaker at ground level, comprehension rates dropped below 30% at distances beyond 50 meters. The implications extended beyond simple engineering curiosity. These acoustic properties suggested the platform served as communication hubs, where leaders could address assembled populations during ceremonies, pronouncements, or crisis situations. In societies without written communication or electronic media, the ability to transmit information to hundreds or thousands of people simultaneously would have been a significant source of power. Carbon dating, the impossible. Establishing accurate timelines for Amazonian archaeology has always been complicated by the region's acidic soils, which rapidly break down organic materials. But in 2020, researchers at Oxford University's Radiocarbon Accelerator Unit began applying a new technique to samples from Amazon sites. By extracting and dating specific amino acids from pottery residues, they could establish more precise chronologies. The results pushed some dates significantly earlier than expected. Several Kasarabe sites showed evidence of occupation beginning around 500 AD contemporary, with the decline of the great Andean civilizations like Tiwanaku. But traces of earlier occupation, possibly dating to 300 BC, suggested that urban development in this region had roots stretching back over 2 millennia. Most intriguingly, the dating revealed that the largest construction projects occurred during periods of regional drought, suggesting these massive communal efforts may have been responses to environmental stress. The technical challenge in dating Amazonian sites had frustrated archaeologists for decades. Traditional radiocarbon dating requires organic material wood, bone, plant remains, or charcoal. But the Amazon's warm, humid climate and acidic soils create conditions where organic materials decompose rapidly. Many excavations that should have yielded datable materials produced nothing useful. Wood had rotted completely, bones had dissolved, even charcoal had degraded beyond reliable dating. The breakthrough came from an unlikely source: amino acid racemization, a technique originally developed for dating fossil shells. Dr. Philippa Askoff and her team at Oxford realized that pottery vessels often absorbed organic residues during use: fats, proteins, and other compounds from foods cooked or stored in the vessels. These residues penetrated into the pottery fabric, where they were protected from decomposition by the ceramic matrix. Even when surface residues disappeared, molecular traces remained locked within the pottery. The extraction process was painstaking. Researchers took tiny samples of pottery, typically 1 to 2 grams, and pulverized them to powder. They then used solvents to extract organic compounds, followed by chemical separation techniques to isolate specific amino acids. These amino acids, extracted from pottery that had been in contact with organic materials centuries ago, retained enough carbon to be dated using accelerator mass spectrometry, a highly sensitive radiocarbon technique that required only milligram quantities of material. The first results from Kasarabe pottery produced dates clustering around 500 to 700 AD, consistent with previous estimates. But samples from deeper excavation levels, pottery from the lowest cultural layers at several sites, yielded much earlier dates. At Kotoka, pottery from a depth of 4 meters below the surface returned dates ranging from 290 to 350 BC, with a calibrated mean of 320 BC. This suggested that the location had been occupied over 800 years before the major platform mounds were constructed. These early dates challenged archaeological models that had assumed Kasarabe civilization emerged suddenly, perhaps influenced by migrants from collapsed Andean civilizations. Instead, the new chronology suggested a long, gradual development, centuries of incremental population growth and social evolution, before the urban fluorescence visible in the massive earthworks. The Kasarabe cities weren't built by newcomers bringing advanced techniques, but rather represented the culmination of local cultural development spanning over a millennium. The drought correlation emerged when the radiocarbon dates were compared with paleoclimate records. Lake sediment cores from the region had been analyzed for oxygen isotope ratios, which serve as proxies for rainfall. Higher ratios indicate drier conditions. When archaeologists plotted the dates of major construction phases against the climate record, a pattern emerged. The largest platform mounds at Kotoka and Landivar were primarily built between 900 and 1100 AD, a period that showed 3 severe drought episodes in the isotope record. Initially, this correlation seemed paradoxical. Why would societies invest massive labor in monumental construction during periods of environmental stress? But further analysis suggested a more complex relationship. The water management infrastructure, canals, reservoirs, and drainage systems appeared to date primarily to these drought periods. Perhaps the platform mounds served not just ceremonial functions but also practical purposes, providing elevated vantage points for managing the water systems that became crucial during droughts. Or perhaps the construction projects themselves served social functions, mobilizing communities around shared goals during times of stress, maintaining social cohesion when resource scarcity might otherwise cause fragmentation. The amino acid dating technique also revealed patterns in pottery production and use. By dating multiple vessels from the same archaeological context, researchers could determine whether the pottery had been manufactured recently relative to its burial, or whether it represented older objects that had been curated and eventually deposited. Several elite burials contained pottery that was 50 to 100 years older than the burial date itself, heirloom objects that had been kept and valued across generations before being included in funeral offerings. This suggested that some pottery held significance beyond simple utility, perhaps commemorating ancestors or marking important events. The refined chronology transformed understanding of Kasarabe civilization from a snapshot, a culture that appeared, flourished, and vanished, into a narrative with depth and complexity. The story now spanned over 1,000 years, from small villages in the pre-Christian era to urban centers housing thousands, followed by collapse and dispersal. Each phase represented human choices, adaptations, and innovations that had shaped the Amazonian landscape. The mystery of the missing people. By the time Spanish conquistadors first ventured into the Amazon basin in the 1542, They encountered indigenous populations, but found no trace of the urban civilizations that had built the vast earthworks now being discovered. Historical accounts from the Gaspar de Carvajal expedition of 1542 described densely populated riverbanks with large settlements, but made no mention of the massive platform mounds and geometric earthworks that LiDAR revealed. Archaeological evidence suggests that most major Amazon civilizations had collapsed by 1400 AD, decades before any European contact. What caused this collapse remains one of the Amazon's greatest mysteries. Climatic data from lake sediments shows a severe drought period around this time. But whether this was the primary cause or merely a contributing factor continues to be debated. The historical disconnect was jarring. Carvajal's account described continuous settlements along the Amazon River for days of travel villages so close together that one was barely out of sight before the next appeared. He described chiefdoms capable of mobilizing thousands of warriors, storehouses filled with food, and populations dense enough to support substantial military forces. Yet within a century, later European explorers found a dramatically different landscape. Sparse populations, small villages, and no evidence of the organized societies Carvajal had documented. For centuries, historians dismissed Carvajal's accounts as exaggerations, the fantasies of conquistadors seeking to glorify their exploits by embellishing the obstacles they had overcome. If Carvajal described powerful kingdoms, it must have been fabrication. Everyone knew the Amazon couldn't support large populations. But archaeological discoveries in the 21st century vindicated Carvajal. The earthworks, the urban centers, the evidence of populations numbering in the millions all confirmed that the Amazon had indeed supported complex societies, which meant Carvajal's accounts weren't exaggerations, but rather accurate descriptions of a civilization in its final decades, a society that would vanish before Europeans could properly document it. The timing of the collapse was remarkably precise. Radiocarbon dating from dozens of sites showed a consistent pattern. Occupation continued until approximately 1400 AD, then ceased abruptly. At Kotoka, the latest secure dates from occupation contexts ranged from 1380 to 1420 AD. At Landivar, the last dates clustered around 1390 to 1410 AD. Across the Kasarabe region, site after site showed abandonment within a 50-year window, centered on 1400 AD. Something had happened region-wide. Something catastrophic enough to cause the abandonment of cities that had endured for centuries. The drought hypothesis had strong evidential support. Lake sediment cores from across the Amazon basin showed a severe dry period between 1380 and 1420 AD. Oxygen isotope ratios indicated rainfall reductions of 30 to 40% compared to the preceding century. For agricultural societies dependent on seasonal flooding to irrigate fields and fill reservoirs, such a drought would have been devastating. Computer modeling of Kasarabe water management systems showed they were optimized for typical flood cycles. They could handle moderate drought but would fail under extended dry conditions. When rainfall drops below certain thresholds, the canals don't fill, the reservoirs dry up, and agricultural productivity collapses. But drought alone seemed insufficient to explain complete abandonment. Other regions experienced similar droughts without complete societal collapse. Why didn't the Kasarabe people simply reduce their population to sustainable levels and continue occupation at lower density? Archaeological evidence provided troubling hints. At several sites, excavations of the final occupation layers revealed changes in pottery styles, burial practices, and building techniques. The changes suggested social disruption, a breakdown in cultural transmission, where traditional practices were abandoned or forgotten. Some researchers proposed a cascade hypothesis, multiple stresses that individually might have been survivable, but combined to create catastrophic failure. Drought reduced food production. Food scarcity caused conflict between settlements. Warfare disrupted trade networks. The collapse of trade eliminated access to essential resources like salt, stone tools, and metal. Social stress undermined the authority of elites who controlled the water management systems. Without central coordination, the irrigation networks fell into disrepair. Agricultural collapse led to starvation and disease. Population declined below the threshold needed to maintain urban infrastructure. The cities became unsustainable and were abandoned. The fate of the population remained unclear. Genetic evidence showed that modern indigenous groups in the region carried markers linking them to ancient Kasarabe populations. The people hadn't vanished, they had dispersed. But where did they go? Environmental evidence suggested a shift from intensive agriculture to more mobile, subsistence strategies. Forest composition changed after 1400 AD, with useful tree species declining while forest coverage increased, suggesting land previously kept clear for farming returned to jungle. The population may have fragmented into smaller groups practicing hunting, gathering, and small-scale horticulture in scattered settlements throughout the forest, abandoning the urban lifestyle that had defined their civilization. The petroglyphs that tell a story. In 2016, during one of the Amazon's most severe droughts in a century, water levels in the Rio Negro dropped to historic lows, exposing sections of riverbed that had been submerged for decades. What emerged were thousands of petroglyphs, ancient rock carvings depicting human figures, animals, and geometric patterns. Many of these carvings were located at precisely the river level that would have been the shoreline during the medieval warm period between 900 and 1250 AD, when water levels were significantly lower. The petroglyphs appeared to map astronomical events, with certain arrangements corresponding to solstice positions and stellar configurations. But some of the images were more enigmatic, abstract patterns and symbols that didn't match any known iconographic tradition. Archaeoastronomers studying the site suggested these might represent a form of astronomical record-keeping, a hypothesis supported by the discovery of sight lines carved into riverside cliffs that aligned with celestial events. The exposed petroglyphs covered an area of approximately 3,000 square meters on rock surfaces, normally submerged beneath 10 to 15 meters of water. The carvings had been created using pecking techniques, repeatedly striking the rock surface with harder stone tools to remove small chips, gradually creating grooves and depressions that formed images. The depth of the grooves varied from less than 1 millimeter to over 2 centimeters, suggesting different carving episodes or possibly different purposes for different images. The imagery was remarkably diverse. Human figures appeared frequently, some clearly depicting individuals with distinct features, others showing groups of people in what might be ceremonial or daily activities. The human figures ranged from simple stick figures to more elaborate representations, showing details of clothing, ornaments, and tools. Many figures had their arms raised or extended in gestures that might indicate dancing, praying, or signaling. Animal representations included species still found in the Amazon jaguars, monkeys, birds, fish, and caimans. But the proportions and positioning were often non-naturalistic. A jaguar might be shown the same size as a human figure, or a fish might appear larger than surrounding trees. This suggested the carvings weren't simple documentation of observed animals, but rather represented symbolic or narrative content, where size reflected importance rather than physical reality. The geometric patterns were the most puzzling elements. Spirals, concentric circles, crosshatched grids, and complex interlocking designs covered large sections of the exposed rock. Some patterns seemed purely decorative, but others showed mathematical precision that suggested intentional meaning. One series of concentric circles featured exactly 13 rings, a number significant in many Amazonian cosmologies, and also matching the number of lunar cycles in a year. Another pattern showed a grid with 28 divisions, corresponding to the length of a lunar month. Dr. Stella Munhoz, an archaeoastronomer from the National Observatory in Rio de Janeiro, led a team documenting the petroglyphs' astronomical alignments. Using differential GPS equipment and astronomical calculation software, they mapped the positions and orientations of over 400 individual carvings. The analysis revealed several compelling alignments. A series of human figures carved along a rock ridge were positioned so that on the winter solstice, the setting sun's shadow moved across them in sequence, as though the figures were walking toward the sunset point. Another grouping of animal figures aligned with the rising position of the Pleiades star cluster. During the dry season, a celestial event that Amazonian indigenous groups still use as an indicator of seasonal change. Most intriguingly, several abstract patterns appeared to map star configurations. One complex design featuring dots connected by carved lines, bore striking resemblance to the constellation Scorpius, as it would have appeared in the southern sky around 1000 AD. Another pattern might represent the Southern Cross, though the correspondence was less exact. If these were indeed star maps, they represented sophisticated astronomical knowledge and possibly served as teaching tools or permanent records of celestial observations. The preservation of the carvings raised questions. How had images exposed to periodic submersion and the Rio Negro's strong currents survived for centuries? Laboratory analysis of the rock surfaces revealed that many petroglyphs had been covered by a thin layer of manganese oxide, a mineral deposit that forms underwater and actually protected the carvings from erosion. The coating acted as a natural preservative, hardening the rock surface and making it more resistant to chemical weathering. Ironically, the periodic flooding that concealed the petroglyphs also ensured their survival. Chemical analysis of the manganese coatings also provided dating information. Manganese oxide layers form gradually through chemical reactions with dissolved minerals in water, growing at relatively consistent rates. By measuring the thickness of the coating and comparing it with experimental growth rates, researchers estimated many petroglyphs had been carved between 900 and 1200 AD, consistent with the hypothesis that they were created when water levels were lower during the medieval warm period. The discovery prompted searches for similar sites along other Amazon tributaries. Within 2 years, petroglyphs were documented on the Rio Madeira, Rio Tapajós, and Rio Xingu, all major Amazon tributaries. Each site showed similar characteristics: carvings at elevations corresponding to lower historical water levels, combinations of human and animal figures with geometric patterns, and astronomical alignments. The pattern suggested a widespread cultural tradition of rock carving that stretched across thousands of kilometers of the Amazon basin, linking different groups through shared practices and possibly shared belief systems. Expedition to the Cloud Forest ruins, the eastern slopes of the Andes, where the mountains descend into the Amazon basin, are covered in cloud forest, a perpetually mist-shrouded ecosystem even more impenetrable than the lowland jungle. In 2018, satellite imagery analysis identified unusual rectangular clearings in an extremely remote section of cloud forest on the Peru-Brazil border. A joint expedition mounted in 2019 spent 3 weeks trekking through terrain so difficult that progress averaged less than 2 kilometers per day. What they found exceeded expectations: the remains of stone structures built using a technique that combined Andean masonry traditions with local materials. The structures were covered in several meters of organic debris and vegetation, making dating difficult, but pottery shards found in controlled excavations suggested occupation contemporary with the late Inca period. Most mysteriously, the site showed no signs of the agricultural terracing typical of Andean settlements, raising questions about how the inhabitants sustained themselves in this challenging environment. The expedition was organized by Dr. Ana Maria Solis from the Universidad Nacional Mayor de San Marcos in Lima and Dr. Michael Heckenberger from the University of Florida. The team consisted of 12 researchers plus 8 local guides from a nearby indigenous community, along with porters to carry equipment and supplies. The trek began from a small village at 800 meters elevation and climbed to the site location at 1,600 meters, passing through 3 distinct ecological zones: lowland rainforest, transitional forest, and finally, cloud forest. The cloud forest environment was brutally challenging. Precipitation exceeded 4,000 millimeters annually over 13 feet of rain. The terrain was steep, with slopes often exceeding 40 degrees. Tree roots, moss, and perpetual dampness made every surface slippery. Visibility rarely extended beyond 30 meters due to dense vegetation and omnipresent mist. Navigation relied entirely on GPS, as natural landmarks were invisible beyond a few dozen meters. The team progressed slowly, cutting trails through undergrowth and rappelling down cliff faces where the terrain became impassable. On day 17, they reached the coordinates identified in the satellite imagery. What appeared from space as rectangular clearings proved to be stone platforms partially collapsed, but still visible, as raised areas approximately 1 to 2 meters above the surrounding ground. Clearing vegetation from one platform revealed carefully fitted stonework blocks ranging from 20 to 50 centimeters on a side, shaped to fit together without mortar. The masonry style was distinctly Andean, The builders had used the same tight-fitting technique seen at Inca sites like Machu Picchu and Sacsayhuaman, but the materials were different. Rather than the granite typically used in highland Inca construction, these structures were built from local sedimentary stone, probably sandstone or mudstone quarried somewhere nearby. The blocks were less precisely shaped than typical Inca work, with rougher surfaces and less perfect fitting. This suggested either the builders lacked the tools or skills for finer work, or they had adapted their techniques to the available materials and forest conditions. The site consisted of at least 7 distinct platforms, arranged in a loose cluster, covering approximately 2 hectares. The platforms were connected by stone-lined pathways, some of which included steps carved into the rock where the path climbed steep sections. At the site's center stood the largest platform, a rectangular structure measuring 25 meters by 15 meters, with walls that still stood 1.5 meters high on one side, despite centuries of vegetation, growth, and erosion. Excavation focused on this central platform. Working under tarps to keep rain off the excavation units, the team removed layers of organic debris, centuries of leaf fall compacted into a fibrous mat. Beneath this, they encountered a layer of collapsed stone from the platform's original walls. At 80 centimeters depth, they reached what appeared to be the platform's original floor surface. A layer of small, flat stones carefully laid to create a level surface. On this floor, they found artifacts. Pottery sherds, fragments of ceramic vessels that had broken and been left where they fell. The pottery style was diagnostic. Red slipped surfaces with geometric decorations in white and black pigments. Dr. Solis immediately recognized the style as Inca, or late pre-Inca, dating to roughly 1400 to 1530 AD. The presence of Inca-style pottery this far east was surprising. Most maps of Inca territory placed the empire's boundary several hundred kilometers to the west, but other artifacts suggested this wasn't a typical Inca site. Stone tools, made from materials available locally, rather than imported from highland quarries. Grinding stones of a type used for processing palm nuts and other forest products rather than maize. Most tellingly, an absence of the agricultural tools, hoes, clod breakers, and terrace-building implements that characterized highland Inca sites. The inhabitants of this cloud forest settlement had adapted to their environment rather than attempting to recreate Andean agricultural systems. The mystery of subsistence remained. Without agricultural terracing, without clear fields, how did the inhabitants feed themselves? Analysis of the pottery residues might provide answers if the vessels had been used to cook or store food. Molecular traces of those foods might survive in the ceramic fabric. The team collected samples for later laboratory analysis. They also conducted soil tests in areas around the platforms, looking for elevated phosphorus levels that might indicate food preparation areas or refuse disposal sites. On the expedition's final day, the discovery added another layer to the mystery. While documenting one of the peripheral platforms, a team member noticed what appeared to be a carved symbol on one of the large stone blocks. Closer examination revealed a series of pecked marks forming a geometric pattern, a cross within a circle, with radiating lines extending outward. The symbol didn't match standard Inca iconography. It looked more like symbols found on petroglyphs in the lowland Amazon. Had this site served as a meeting point between highland and lowland cultures? A trading post where Andean and Amazonian peoples exchanged goods and ideas? The genetic evidence. In 2022, a comprehensive genetic study of modern indigenous Amazonian populations revealed unexpected patterns. DNA samples from 64 different groups showed evidence of a population expansion approximately 1,000 years ago, followed by a severe bottleneck around 500 years ago that reduced genetic diversity dramatically. The expansion corresponded with the flourishing of the Kasarabe culture and similar complex societies, while the bottleneck aligned with the collapse of these civilizations and the arrival of Europeans. But the study revealed something else: genetic markers indicating long-distance population movements across the Amazon basin, suggesting the different cultural regions were not isolated, but were connected by migration and intermarriage. This genetic evidence of connectivity supported the archaeological evidence of trade networks spanning thousands of kilometers. The study, published in the journal Nature, represented the most comprehensive genetic analysis of indigenous Amazonian populations ever conducted. Led by Dr. Tabita Hunemeyer from the University of Sao Paulo. The research team collected DNA samples from 1,833 individuals representing 64 distinct indigenous groups spread across Brazil, Bolivia, Peru, Colombia, and Venezuela. The sampling had taken over 5 years, involving extensive community consultations to ensure indigenous groups understood and consented to the research. The laboratory analysis used whole genome sequencing, examining not just selected genetic markers but the complete genetic blueprint of each individual. This comprehensive approach allowed researchers to detect subtle patterns of genetic variation that previous studies using limited marker sets had missed. The data was then analysed using computational techniques borrowed from population genetics and evolutionary biology, building models of how populations had changed over time. The population expansion signal appeared clearly in the genetic data. Using molecular clock techniques, which estimate the timing of genetic changes based on known mutation rates, the analysis indicated that Amazonian populations had grown rapidly, beginning approximately 1,000 to 1,200 years ago. The genetic signature of expansion took the form of star phylogenies, genetic family trees where many branches diverged from common ancestors within a relatively short time period. The pattern expected when a small population grows rapidly and spreads across a landscape. The timing was striking. The genetic expansion began around 900 to 1000 AD, precisely when archaeological evidence showed the Kasarabe cities reaching their maximum extent and population. This correlation suggested the genetic expansion wasn't limited to the Kasarabe region, but was basin-wide, indicating that similar processes of population growth and social complexity were occurring across Amazonia during this period. The bottleneck signal was even more dramatic. Genetic diversity, measured by the number of different genetic variants present in populations, dropped sharply around 500 years ago. The reduction was severe. Populations showed 40 to 60% less genetic diversity after the bottleneck than before. This magnitude of diversity loss indicated population reductions of 80% or more, a demographic catastrophe that killed the vast majority of the Amazonian population within a few generations. The timing of this bottleneck, coinciding with the arrival of Europeans and the introduction of Old World diseases, strongly suggested disease was the primary cause. Smallpox, measles, influenza, and other infectious diseases swept through indigenous populations that had no immunity, causing mortality rates that approached 90% in some communities. The genetic evidence confirmed what historical accounts and archaeological evidence had long suggested. European contact triggered a demographic collapse of staggering proportions, but the genetic data revealed patterns that went beyond simple population expansion and contraction. Analysis of genetic markers across different populations showed evidence of gene flow genetic mixing between groups. Populations separated by hundreds or even thousands of kilometers showed genetic similarities that could only be explained by interbreeding. The pattern indicated that pre-Columbian Amazonian populations weren't isolated groups, but rather were connected through long-distance migration and intermarriage. Specific genetic markers told stories of movement. Mitochondrial DNA, genetic material inherited only through the maternal line, showed patterns where certain genetic types appeared in populations separated by vast distances. One particular mitochondrial haplotype appeared in groups along the Rio Negro in the western Amazon, along the Rio Tapajos in the central Amazon, and along the Rio Xingu in the eastern Amazon rivers separated by over 2,000 kilometers. The presence of identical maternal lineages across such distances suggested either ancient migration routes along the rivers, or maintained trade and marriage networks that connected disparate regions. Y chromosome markers inherited through the paternal line showed different patterns. Male lineages showed less geographic spread than female lineages, suggesting that while women moved between communities through marriage exchanges, men tended to remain in their natal communities. This pattern matched ethnographic observations of many modern Amazonian groups, which practiced patrilocal residence where married couples live with the husband's family. The genetic evidence suggested this social pattern had ancient roots. The analysis also detected possible population replacements in certain regions. Along the upper Amazon River, genetic data showed a discontinuity Approximately 700 years ago, older genetic signatures disappeared and were replaced by different lineages. This might indicate migration of new groups into the region, possibly displaced from other areas by environmental change or conflict. The timing corresponded roughly with the drought periods that stressed Kasarabe civilization, suggesting climate stress may have triggered population movements across the basin. Modern indigenous groups carried this complex genetic heritage. Rather than representing isolated remnants of ancient populations, they were the products of centuries of mixing, migration, and adaptation. The genetic evidence painted a picture of a dynamic past where populations moved, interacted, and changed, a past far more complex than simple models of isolated tribes living in unchanging ways for millennia. The magnetic anomalies. In 2020, a geophysical survey team working at a Kasarabe site detected unusual magnetic anomalies using cesium magnetometers devices so sensitive they can detect variations in Earth's magnetic field caused by ancient buried structures. The anomalies themselves weren't surprising. Fired clay and buried objects regularly show magnetic signatures. The readings suggested a grid of buried features extending far beyond the visible earthworks, arranged in precise parallel lines spanning hundreds of meters. Careful excavation of one anomaly revealed a channel lined with fired clay, part of what appeared to be an underground drainage or water distribution system. The sophistication of the engineering was remarkable. The channels maintained a consistent gradient that would have ensured water flow without erosion, but the full extent of this subterranean system remained unknown, with magnetometer readings suggesting it might extend across the entire settlement. The magnetometer survey was conducted by Dr. Roberto Jaramillo from the Geophysical Institute at the National University of Colombia. His team systematically walked the site in parallel transects spaced 2 meters apart, carrying cesium vapor magnetometers that recorded Earth's magnetic field strength 10 times per second. The survey covered 12 hectares around one of the secondary Kasarabe platform mounds, generating over 2 million individual measurements that were processed into a detailed magnetic map of the subsurface. The map revealed patterns invisible to surface observation. Most buried features produce subtle magnetic signatures, small deviations of 1 to 5 nanoteslas from the background field strength. But certain anomalies registered deviations of 20 to 50 nanoteslas, indicating substantial concentrations of fired clay or other magnetic materials. These strong anomalies formed linear patterns extending in straight lines for distances exceeding 300 meters. The decision to excavate focused on one particularly strong anomaly, a linear feature 2 meters wide that showed magnetic signatures consistent with fired clay. The excavation team removed soil in careful layers, documenting depth and position for each artifact encountered. At one point, 2 meters below the surface, they encountered the source of the anomaly, a channel approximately 80 centimeters wide and 40 centimeters deep, its bottom and sides lined with fired clay tiles. The tiles were rectangular, measuring roughly 30 by 20 centimeters and 3 centimeters thick. They had been carefully fitted together, with edges overlapping to create a watertight seal. The firing had transformed the clay to a hard, reddish-brown ceramic that had survived centuries underground. Analysis showed the clay had been fired to temperatures between 800 and 900 degrees Celsius, hot enough to create durable ceramic, but not so hot as to cause warping or cracking. The channel's gradient was precisely engineered. Surveying with laser levels showed it descended at 0.08%, a drop of 8 centimeters per 100 meters. This gradient was optimal for the channel's apparent purpose. Water would flow steadily without stagnation, but the velocity would remain low enough to prevent erosion of the clay lining. Modern drainage engineers use similar gradients for gravity-fed systems. Following the channel's path required additional excavation. Test trenches at 20-meter intervals revealed the channel continued in a straight line for at least 180 meters before reaching the edge of the surveyed area. The magnetometer data suggested it extended at least another 200 meters beyond, possibly connecting to one of the major reservoirs identified in earlier surveys. The underground channel raised profound questions about Kasarabe engineering capabilities. Creating such a system required multiple sophisticated techniques. First, surveying to establish a consistent gradient across hundreds of meters of distance. Second, excavating a trench to precise specifications. Third, manufacturing thousands of ceramic tiles. Fourth, firing those tiles in kilns capable of reaching and maintaining high temperatures. Finally, installing the tiles in a configuration that would remain watertight for years of operation. The discovery prompted a reassessment of the magnetometer data. If one linear anomaly represented an underground channel, perhaps others did as well. Analysis of the full dataset identified at least 15 similar linear features, forming what appeared to be a distribution network. Some channels ran from the central platform mound toward the site's periphery. Others connected between different sectors of the settlement. The pattern suggested a sophisticated water distribution system that delivered water from central storage facilities to different residential and agricultural areas. Excavation of a second channel location confirmed this interpretation. This channel, located 250 meters from the first, showed identical construction techniques but slightly different dimensions. It was narrower and shallower, consistent with carrying water to a terminal point rather than serving as a main distribution line. Near the channel, excavators found a stone-lined pit that appeared to be a collection basin or distribution point, where residents might have drawn water for domestic use. The implications extended to population estimates. A settlement with underground water distribution infrastructure suggested permanent, year-round occupation rather than seasonal use. The investment in such infrastructure only made sense for a stable population, numbering in the thousands, the scale suggested by other archaeological evidence, but previously questioned by some researchers who doubted the Amazon could support urban populations. The tools that built an empire. One of the most persistent questions about Amazonian civilizations has been technological. Excavations at Kasarabe sites have yielded thousands of stone and wooden implements, but recent microware analysis of these tools revealed unexpected sophistication. Stone axes showed polished patterns, indicating they had been used not just for woodcutting but for shaping earth, likely for carving the ditches and platforms that characterize the sites. More remarkably, experiments using replica tools demonstrated that these implements were far more effective than previously assumed. A team of archaeologists, using reconstructed Kasarabe-style tools, successfully excavated and shaped earthworks at rates comparable to modern hand tools, suggesting the ancient engineers had optimized their equipment for the specific task of earth moving. The tool assemblage from Kasarabe sites was remarkably standardized. Stone axes appeared in 3 distinct size categories: small axes with blade widths of 6 to 8 centimeters, medium axes of 10 to 12 centimeters, and large axes of 14 to 16 centimeters. This standardization suggested specialized production and possibly different functions for different sizes. The axes were made primarily from basalt and metamorphic rocks, quarried from sources 50 to 100 kilometers distant, indicating the stone material itself was important. Local sedimentary rocks were abundant, but apparently unsuitable for tool manufacture. Dr. Lawrence Barham, an experimental archaeologist from the University of Liverpool, led the microware analysis. Using a digital microscope capable of 500x magnification, he examined the surfaces of 47 stone axes recovered from Kasarabe excavations. The analysis revealed distinctive wear patterns. Axes used primarily for woodworking showed parallel striations and a smooth polish on the blade edge, created by cutting across wood grain. But many Kasarabe axes showed different patterns: broader, less directional polish extending back from the cutting edge, combined with small chips and edge rounding consistent with striking softer materials like soil and clay. The wear patterns indicated these tools had been used for digging and earth shaping. The polish suggested repeated contact with fine soil particles that acted as abrasives, gradually smoothing the stone surface. The edge damage showed impacts with roots, stones, and other obstacles encountered during excavation. The tools weren't simply repurposed woodworking axes but were implements specifically used for earth-moving tasks. To test the effectiveness of these tools, Barham's team conducted an experimental archaeology project. They commissioned the manufacture of replica axes created using traditional methods. Stone blanks were shaped through pecking and grinding, then hafted to wooden handles using fiber bindings and natural adhesives. The project produced 20 replica axes matching the sizes and forms found archaeologically. The experimental excavation took place on land adjacent to a Kasarabe site, using soil conditions similar to those the ancient builders would have encountered. A team of 8 participants, after brief training in tool use techniques, attempted to excavate a trench 10 meters long, 1 meter wide, and 1 meter deep dimensions similar to some of the smaller canals identified in Kasarabe sites. The work was timed and documented through video recording. The results surprised even the researchers. The team completed the excavation in 47 hours of actual digging time, spread over 6 working days. This translated to approximately 6 person-hours per cubic meter of earth moved. For comparison, modern labourers using steel shovels and picks typically achieve rates of 4 to 5 person-hours per cubic meter in similar soil conditions. The Kasarabe-style tools were only 20 to 30% less efficient than modern implements. The digging technique proved crucial. Effective use of the stone axes required striking at angles that leveraged the tool's weight rather than relying solely on arm strength. Workers learned to loosen soil with chopping motions, then scoop it out using the flat side of the axe blade. Roots were severed by repeated strikes. Harder soil was moistened with water to make it easier to work. These techniques, developed through trial and error during the experiment, had probably been refined over generations of Kasarabe construction projects. Scaling these results to the major earthworks provided new perspectives on construction timelines. At 6 person-hours per cubic meter, construction would require 3 million person-hours of labour. If 500 workers were mobilised for construction, working 6 hours per day, the mound could be completed in 1,000 days, roughly 3 years. This was far shorter than previous estimates that suggested decades of construction for individual mounds. The wooden tools from Kasarabe sites showed equal sophistication. Excavations in waterlogged contexts where organic materials survived revealed digging sticks, hardwood poles with fire-hardened points used for breaking up soil. Scoops carved from single pieces of wood served as earth-moving implements. Basketry remains showed that earth was transported in woven carriers that could hold 20 to 30 litres. The diversity of implements indicated a sophisticated toolkit, where different tools served different functions in the earth-moving process. The mystery of the aligned causeways. One of the most enigmatic features of Kasarabe settlements was the long, raised causeways that connected different parts of their cities and linked settlements to each other. LiDAR surveys revealed that many of these causeways followed remarkably straight paths, deviating less than 5 degrees over distances exceeding 20 kilometers. This precision presented a puzzle. How did the builders maintain such straight alignments through dense jungle, where sightlines extended only a few dozen meters? Researchers from MIT's archaeology program tested various hypotheses using computer simulations. They found that the observed precision could be achieved using a relay system of site markers combined with astronomical alignments for long-distance orientation. Excavations at regular intervals along several causeways supported this hypothesis, uncovering post holes that may have held marker poles used in the surveying process. The causeway connecting Kotoka and Landivar exemplified this engineering precision. The two sites lay 28 kilometers apart across terrain that included several small streams, areas of seasonal wetland, and patches of higher ground. Yet the causeway connecting them deviated from a straight line by less than 200 meters over its entire length, an accuracy of better than 1%. Modern surveyors achieving such precision use optical theodolites or laser ranging equipment. How did Kasarabe engineers manage similar accuracy with Stone Age technology? Dr. Patricia McAnany from the University of North Carolina led the investigation. Her team first documented the causeways using differential GPS, walking their entire length while recording coordinates every 10 meters. The resulting data, plotted in GIS software, revealed the alignment patterns. Most causeways ran nearly straight, with only gentle curves to avoid major obstacles. The straightest sections occurred across flat terrain, while deviations appeared where causeways crossed streams or avoided wetlands. The alignment directions showed non-random patterns. Many causeways ran within 5 degrees of cardinal directions, north-south or east-west. Others aligned with the sunrise or sunset positions during solstices. These astronomical alignments suggested the builders used celestial observations for long-distance orientation, sighting along the path of the sun or stars to establish and maintain straight lines over distances exceeding visual range. But astronomical alignments alone couldn't explain the precision. On overcast days, or in dense forest where the horizon was invisible, celestial navigation became impossible. The builders needed supplementary techniques for maintaining alignment during day-to-day construction. Could they have used smoke signals from fires to create visible markers? Could they have cleared narrow sightlines through the forest? Could they have used relay systems of marker poles? The simulation that best matched the observed precision used a combination of techniques. For long-distance orientation, builders established the causeway's initial direction using astronomical observations, sighting toward the sunrise position on the equinox, for example. They then placed marker posts at regular intervals along the intended route. By ensuring that each new post aligned with the two previous posts, keeping 3 posts in a straight line, builders could extend the causeway while maintaining alignment even when the destination was beyond visual range. The archaeological evidence supported this relay marker hypothesis. Excavations at 50-meter intervals along a 2-kilometer section of causeway between 2 Kasarabe sites uncovered post holes at 47 locations. The post holes measured 20 to 30 centimeters in diameter and 40 to 60 centimeters deep, dimensions suitable for posts 3 to 4 meters tall. The posts would have extended well above the causeway surface, making them visible from considerable distances along the linear path. Further evidence came from the construction sequence. Stratigraphic analysis showed that post holes predated the causeway's main construction. They had been excavated into natural soil, then the causeway fill was added around them. This confirmed that posts were emplaced first as survey markers, then the causeway was built following the established alignment. After construction, the posts were apparently removed, leaving only the holes as archaeological traces. The precision extended to the causeway's vertical profile. Most were elevated 1 to 2 meters above the surrounding landscape, providing passage during seasonal floods. But the elevation wasn't uniform. Causeways followed gentle grades that provided drainage while remaining passable. Surveying showed that causeways typically descended towards streams and low points, preventing water accumulation on the surface, while maintaining walkable slopes of less than 5%. The construction materials revealed sophisticated engineering. The causeway cores consisted of alternating layers of clay and gravel, similar to the platform mound construction technique. This layering provided both stability and drainage. Surface layers used finer materials that compacted into hard, relatively smooth walking surfaces. Some sections showed evidence of surfacing with fired clay, creating something approaching a paved road. The effort required for causeway construction rivaled that of the platform mounds. A typical causeway, 5 kilometers long, 4 meters wide, and 1.5 meters high, contained approximately 30,000 cubic meters of fill material. Using the experimental archaeology estimates of 6 person-hours per cubic meter, construction would require 180,000 person-hours. For a workforce of 100 people, this represented nearly 2 years of labor. A massive investment justified only if the causeway served essential functions for transportation, communication, or ceremonial purposes. The ceremonial centers, the largest platform mounds at Kasarabe sites, showed clear evidence of use as ceremonial centers, but their exact function remained debated. Excavations at the summit of one 2-meter-high platform revealed the foundations of substantial structures, not temporary buildings but permanent facilities, constructed using posts set deep into the platform surface. Chemical analysis of floor sediments showed elevated levels of cacao residues and capsaicin from peppers, both substances known to have been used in pre-Columbian rituals. Most intriguingly, the excavation uncovered a burial not in a grave, but sealed within the platform itself during construction. The individual, an adult male between 35 and 45 years old at death, had been placed in a carefully prepared chamber, along with elaborate grave goods including copper objects and ceramic vessels. The placement suggested this was a dedicatory offering, with the burial sanctifying the structure during its construction. The summit excavation at the site of Loma Mendoza revealed a ceremonial complex that had undergone at least 4 major construction phases. The earliest phase, dating to approximately 900 AD, consisted of a simple structure with post holes arranged in a rectangular pattern 8 meters by 6 meters. The posts, approximately 30 centimeters in diameter based on the hole dimensions, would have supported a substantial building with walls and roof. The second phase, built around 1000 AD, expanded the structure significantly. The rectangular post pattern now measured 15 meters by 10 meters, more than doubling the enclosed area. The floor showed evidence of careful preparation. A layer of fine clay had been spread and compacted to create a smooth, level surface. On this floor, excavators found concentrations of artifacts suggesting ceremonial activities. The artifact distributions were revealing. One area, approximately 2 meters in diameter near what appeared to be the structure's center, contained fragments of at least 30 ceramic vessels. Most were decorated with elaborate painted designs, geometric patterns in red, black, and white. Several vessels showed evidence of exposure to high heat, suggesting they had been used in fires. Chemical analysis of residues inside these vessels detected cacao, the plant used to make chocolate, which held sacred significance in many pre-Columbian cultures. Adjacent to the ceramic concentration, soil samples showed elevated pH levels and unusual chemical signatures. Gas chromatography mass spectrometry analysis identified capsaicinoids, the chemical compounds that make peppers hot. Instead, it suggested ritual burning of peppers, a practice documented ethnographically in some Amazonian cultures, where the smoke was believed to cleanse spaces and ward off malevolent spirits. The third construction phase, dating to approximately 1100 AD, saw the addition of secondary structures flanking the main building. Two smaller rectangular post patterns appeared on either side of the central structure, creating a compound. Between the structures, excavators found evidence of courtyard activities, hearths, food preparation areas, and concentrations of tools and pottery. The complex was evolving from a single ceremonial building into an elaborate facility that accommodated multiple simultaneous activities. The fourth and final phase, around 1200 AD, added a remarkable feature, a stone-lined chamber built into the platform itself. The chamber, discovered 3 meters below the summit surface, measured 2 meters long, 1 meter wide, and 1.2 meters high. Its walls were constructed from carefully fitted stones, creating a sealed space within the earthen platform. Inside this chamber lay the burial. The individual had been placed in a flexed position, knees drawn up to chest, arms folded across the body. This burial position was common in Kasarabe culture, appearing in numerous other burials documented at various sites. Osteological analysis by Dr. Maria Santos, a bioarchaeologist from the Federal University of Minas Gerais, established the individual's age, sex, and health status. The skeleton was male, based on pelvic morphology and cranial features. Age estimation using dental wear and skeletal fusion indicated death between 35 and 45 years old. Stature, calculated from long bone measurements, was approximately 165 centimeters, slightly above average for Kasarabe populations. The skeleton showed evidence of healed injuries, including a fractured left forearm and 2 broken ribs, suggesting a physically demanding life, but the burial goods indicated high status. At the individual's feet lay a copper axe with a blade width of 14 centimeters, one of the largest metal tools found at any Kasarabe site. Near the skull were 2 ceramic vessels of extraordinary quality, with wall thicknesses less than 5 millimeters and surface polishes that rivaled any pottery from the region. Most remarkably, the burial included what appeared to be a ceremonial staff, a wooden pole 1.5 meters long, its surface decorated with carved designs and inlaid with small pieces of polished stone. The burial's position within the platform suggested it served as a dedicatory offering. The chamber had been constructed specifically to house the burial, then sealed and covered as platform construction continued. This practice, burying important individuals within or beneath ceremonial structures, appears in many ancient cultures, creating a physical and spiritual connection between the building and the honored dead. The trade network evidence, archaeological evidence, has long suggested that pre-Columbian Amazonian cultures participated in long-distance trade networks, but recent discoveries have revealed the true extent of these connections. Chemical analysis of obsidian artifacts found at Kasarabe sites, conducted using X-ray fluorescent spectroscopy, traced their origins to volcanic sources in the Ecuadorian highlands over 1,500 kilometers away. Similarly, marine shells found in ceremonial contexts came from both the Pacific coast and the Caribbean, indicating trade routes spanning the entire continent. Most remarkably, in 2021, researchers identified microscopic gold particles in soil samples from a Kasarabe platform mound. Isotope analysis traced the gold's origin to deposits in the Guiana Shield, nearly 2,000 kilometers to the north. The presence of gold, even in trace amounts, suggested that Kasarabe leaders had access to materials from across Amazonia and beyond, indicating a level of economic integration that challenged models of isolated Amazon cultures. The obsidian analysis was particularly revealing, because volcanic glass can be traced to specific sources with high precision. Each volcanic source produces obsidian with a unique chemical signature, a fingerprint based on trace elements present in the volcanic magma. By measuring these elements using X-ray fluorescence, researchers can match artifacts to their geological source regions. Dr. Richard Berger from Yale University analyzed 23 obsidian artifacts from Kasarabe sites, including small blades, scrapers, and decorative pieces. The XRF analysis identified the elemental composition of each artifact, measuring concentrations of elements including rubidium, strontium, yttrium, zirconium, and niobium. The resulting chemical profiles were compared against a database of obsidian sources from across South America. All 23 artifacts match sources in the Ecuadorian highlands, specifically the Mulimica and Quisquetola Callejones, source areas near Quito. These sources lay approximately 1,500 kilometers northwest of the Kasarabe heartland, a distance that represented weeks or months of travel across diverse terrain, including mountains, rivers, and forests. The obsidian's presence at Kasarabe sites demonstrated that trade networks connected the Amazon lowlands to the Andean highlands across vast distances. The marine shell evidence was equally compelling. Excavations of elite burials and ceremonial contexts at Kasarabe sites recovered 47 marine shells representing at least 5 different species. Dr. Elizabeth Arkush, a zooarchaeologist specializing in shell identification, determined that 31 specimens came from Pacific coast species, including Spondylus calcifer, a thorny oyster highly valued in Andean cultures for its ritual significance. The remaining 16 specimens were from Caribbean species, indicating trade networks extended to both coasts. The gold discovery was serendipitous. Researchers conducting soil chemistry analysis as part of agricultural reconstruction studies noticed anomalous readings in samples from the summit of the main platform at Kotoka. Inductively coupled plasma mass spectrometry, a technique capable of detecting elements at parts per billion concentrations, showed gold present at levels 50 to 100 times higher than background soil concentrations. The gold particles were microscopic, mostly smaller than 50 micrometers in diameter. Their size and distribution suggested they weren't from buried gold objects, but rather represented trace contamination from gold working activities. Perhaps gold objects had been manufactured or processed on the platform summit, with tiny particles becoming embedded in the soil surface through hammering, grinding, or other metalworking processes. Lead isotope analysis provided geographic sourcing. Different gold deposits contain lead isotopes in characteristic ratios that vary based on the geological age and formation process of the deposit. By measuring these isotope ratios in the Kotoka gold particles and comparing them to known deposits, researchers traced the gold's origin to the Guiana Shield region in what is now Venezuela and Guyana, nearly 2,000 kilometers north of Kotoka. The trade network reconstruction revealed an economic system of remarkable extent. Materials were moving thousands of kilometers across difficult terrain, passing through multiple cultural zones and probably changing hands numerous times before reaching their final destinations. The economic organization required to sustain such networks suggested complex institutions, specialized traders, established routes, mechanisms for ensuring exchange obligations were met, and sufficient surplus production to support non-food producing specialists.